To kuma bene yake ɗorawa tanki ko a nan ƙasa ne? Ni bene ɗin ƙasa?
So this is like when
A fannin uku ake samu. Fannin uku ake samu ciki ba? Shi ma ya da kasa da rijiyar da kuke da ita. Ni so nake sanin taro. Hai, goma sha biyu. To kenan. Bara lissafa zan kira ka.
Your brain sees you taking those out. So your brain starts to change the way your brain is. If you can't control your own brain, your brain controls you. You gotta tell your brain when you want to go high, you want to go high. You gotta go not over. We believe it's the other way around. No, we put in our minds, we should do.
I like
No,
it.
it's not. No, it's not. No, it's not to play in front of you. No, it's going to play to get out the door.
Na gol. Yau guda goma sha biyu suka zagaye.
are you ready?
My mother named me Farida.
Huh?
I came to Nigeria. I think
Ina ga sha ashirin.
Farida.
Dari uku da nawa. Wanda na siya ina. Nisan wanda na siya zai musu.
Kyar ma suke kula.
Ba zai yi ba. Shi biyu suna ta sai biyu sun wani.
Wani basu da gudu.
Fannin ma ake sa masa.
Sun kai hajiya.
Mutane ne.
babu kwanda ba tamanin kuma da biyu da tamanin amma bana tuni za su samu su guda hudu ah 300 300 guda hudu Hello, Abu, kana jira? Ni 100 Allah ya fara. Ina tsammanin ya sai yana Allah sakon yana
za ta wani za ta ɗauko app ɗin ta za ta ɗauko mata app
sai a yi
yi ta ɗauko ta kuɗin
da akwai wannan me sunan shi Assalamualaikum. Assalamualaikum. Gaskiya ai ka san yanzu ya fi sauki gaskiya ita a lokacin ka tana kai ya fara haya
da sun magana har wannan wannan ya ba bankin da za ka ji ba a kwamfulan da
لا انا قال ابو حتى في
Allah ya samu na wannan wata an kuma matsala sosai so da kaga wannan wata
عشان الله عشان بس
kowane
Okay. Okay. Good evening, everyone. Good morning, good afternoon, good evening from wherever you're watching from. Um, coming. Perfect. Okay, good afternoon, good morning, good evening, everyone. Please, I need to know if you can all hear me. Please, I need to know if you can all hear me. Just drop in the comment section if you know you can hear me, or just react to it and let me know if you can hear me. Okay, okay, okay. Yeah, thank you very much. That's enough. Yeah, I can see you. Thank you very much, all. So, before we start, please kindly unmute yourself. I mean, kindly mute yourself, please. If you know your mic is on, please verify now and please unmute yourself. Secondly, please turn off your camera. Please, your camera might be causing a distraction. Please kindly turn off your camera. Please kindly turn off your camera. I'm majorly speaking to those people who joined via Zoom. Please turn off your camera, please. I'm still seeing some camera being turned on. Mr. Timothy Azanda, your camera is turned on. Kindly turn off your camera, please. If you know your camera is turned on, please kindly turn it off. If you know your mic is on mute, kindly mute it before we proceed, just to avoid any kind of distraction. I'm waiting for you to do that, please. I'm still seeing some camera being turned on. Okay. Yeah, thank you very much for that. All right, all right, all right. Okay. Yeah, it's good to be back again, or it's actually good to see you all again. Thank you again for connecting. Thank you for joining. For those of you who has been actively involved in this program or in this course, I want to say well done. Um, Okay, let's just take 5 minutes to do, to just do something like more like house welcoming and housekeeping. So just put in the comment section how has been the learning so far. This is week 3, which I believe that by now you should be done with course 3, which is actually the remote sensing aspect. So I want to know how your journey has been, how the learning has been. What are the things that maybe you are finding difficult to, navigate around? What are your challenges? So can we do that in the next 5 minutes before we begin? So just drop in the comment section. It's good to see you, Mr. Mefford. I was actually looking for you in the last class. I don't know if you're around in the last class. Brian Mefford, is actually good to see you on the Zoom. Okay, you have to join. Okay, okay, all right, no problem. Thank you. It's good to have you again here. So please, so how has been, okay, so far we are trying to go smoothly, sir. Okay, thank you for that. Okay. Learning has been great. Okay, thank you, Oro Yemi Blessing. Thank you very much. It has been good for now. Okay, thank you, Evidence. Um, no challenges. Okay, which module are we covering today? I haven't really gone far into module 3. Okay, then this is your chance. We are covering module 3 today, which is the introduction to remote sensing. That's what we will be covering today. It has been fantastic. Okay, no challenge. The class has been great. You're a great teacher. Thank you very much. And you're actually a great student as well. Thank you very much. What's the name now? Jessica. Thank you very much, Jessica. It has been amazing, sir. Your videos and slides are detailed. Thank you. Thank you, Mercy Lawan. God bless you. Um, Interesting learning experience. Abdul, thank you very much. Okay, I think that's all for now. Okay, Oluwapamilere, it has been great, especially for someone like me who is new to GIS. Oh, you are really welcome. Thank you very much for that. As a beginner, I need more time and practice for downloading vector data. We'll be covering that aspect today, so just follow up. I have not yet started the remote sensing. Why haven't you started? Anyway, this is actually your chance also to learn. So without wasting much of our time, because we have a lot to do, so let's get right into what we have today. Holy Spirit, help us today. Okay, so this week, we will be looking into, why is my slide not moving? Oh, sorry, I don't know why my slide is not moving. Okay, oh, I have to, no, I need a presentation mode. Mm, is there no presentation mode here? Okay, let me just go ahead. So today we'll be looking into, what's it called now? Fundamentals of remote sensing. Fundamentals of remote sensing. So, okay, even before I begin, I think this was actually part of the assignment for those of you who have actually done the assignment. So, let me just ask briefly that what have you learned so far? If you know you've watched the videos, you've actually done what's it called? You are done with course 3. So let me just ask a brief question. Just drop it on the comment section. What do you now really understand between the difference, or are there even difference between remote sensing and GIS? Is there any difference? If there are difference, shortly just put it on the comment section. I just want to understand our understanding, especially for those of us who have done the assignment, and who is done with the course. I mean the course 3. So just drop it on the comment section. What do you understand by the difference between remote sensing and GIS? Are they the same or they are different? Just shortly, please. I'm looking into the comment section. I'm not seeing anything yet. I'm waiting for your comment. The difference, hope you can still hear me, right? Yeah. The difference between what you understand by GIS and remote sensing. Okay, Miss or Mrs. Brigret said GIS is for data analysis. Okay. And remote sensing is for data collection. Good, good. Okay, okay. You are still on track. Remote sensing involve assessing geographical data without physical contact. You are right. I'm currently working on module module 3 should be done by the end of today. All right, Mr. Medford. Okay. I'm not seeing any other. Remote sensing is the technology of acquiring information about the Earth's surface from a distance, typically via sensors mounted on satellite, aircraft, or drone. Oh, very good, Mr. Clemens. I don't know if that pronunciation is right. Thank you very much for the explanation. Okay, so let's get right into it. Thank you all for your comments. I can see all your comments. Thank you all. So, of course, in this course of this video or this week, I believe that for those of you who are done with the course, you should be able to understand what remote sensing is, the type of remote sensing we have, the platform of remote sensing, the type of resolution, and you should be able to know how or where to actually able to get your data from. So let me try to, before I start, let me try to connect this. I always love I always love, anytime I'm teaching, I always love to connect everything that I'm actually doing. Either it is a series, I always love, I know, I always come to that point where I make sure that everything is actually interconnected. I don't believe in a splitted knowledge. You are learning this and it's not actually connecting to what you are learning. So I always make sure that everything I'm teaching week by week is always connected to the previous week so that it actually makes sense to you. So, last week we talked about special data type, the data management system, and the coordinate system. So why are we jumping into remote sensing? So we need to understand that the special data type that we explained or we talked about last week, there is actually a need for us to be able to get those data. Yeah, we've have the understanding, we've come into the full knowledge or understanding that we have vector data, we have raster data, we have so data, but the question is that how are we going to collect this data? Where are we going to get this data from? And that is exactly what this week actually try to explain and actually solve. That is the question this week module actually solve. So in fact, the beauty about this week is that we are not just looking into how can we able to download that data, but we're also looking about how are these data actually gotten from. So if you are to use maybe satellite data or if you are to use one maybe Landsat data or one imagery like that, I mean, we should be, even though if not the full scope or the full understanding, but at least the basic understanding is that how does this even work? How is this data even generated? What comes about this data? And that is exactly what we are looking into this week. So to answer that question is about this data we are talking about, vector data, raster data, or any kind of data that has to do with special data, how they are being derived. So one of the principles of how they are being derived, most especially when it comes to raster data, it is what we call remote sensing. Remote sensing. So I state here that remote sensing is defined as a science and
Well, no.
While we are waiting for the speaker, how are you guys?
While we are waiting for the speaker, how are you guys?
Good, good. And you?
While we are waiting for the speaker, how are you guys?
How are you guys?
Good, good. And you?
Hey, I don't know. We are very fine.
Yes, we are fine. How are you?
I'm better, Baba.
Wow, that is good.
We are fine, sir.
Very fine.
Thank you, sir.
Oh, it seems like he experienced a bad network, eh?
Yeah.
So, evidence, where are you? You happen to be
Yeah, I think it's network challenge.
I'm in Zimbabwe.
where exactly?
Babora.
Me, I'm in Harare, but at the moment I'm in Bedbridge.
Musadaroka Baba. Data say pane nhamba yenyu.
Eh,
Nyorai
uri
comment
kupi?
section.
Hello, please. This is not, please, we should respect our protocol here. They say we should meet. It's not that we should just continue discussing anything that we feel like. Please,
But you are not the moderator, like I say. You are the moderator. The speaker is not there. We can talk while we are waiting for the speaker. Are you the moderator?
Even though I'm not the moderator, some of you are playing. We have many people here. We have so many things. Please, you should meet yourself. Go back to
Baba,
chat privately.
I think you should get rid of that attitude of the class monitor. Eh?
Yes. Class monitor.
You are here to put order.
I'm the one. I'm here.
Thank you, sir. Come.
I'm the one. I'm here. Class monitor.
What happens? Mbuzi zamasikati zvinombobuda dhoiri rinogona rakashama toya saka ndati aise mucount so that hapana Okay, guys, please let's mute our mic back. Sorry about that. Oh, sorry, hold on. Okay. Okay, guys, sorry about that. My system went off. I didn't know it was not plugged. So are we together again? Sorry, just give me a thumbs up
Yes,
if
go
you can hear
ahead.
me. All right, thank you very much. Please mute your mic back, please. Mute your mic back, especially the people on the Zoom, because your noise might be disturbing the people on the YouTube. Yeah, thank you very much for your patience. So let's get back to it. So I was saying, I was trying to define remote sensing, and I said remote sensing is defined as the art and the science and the art of obtaining an information about an object, area, or any phenomena without making a physical contact. This is the simplest English of the definition of remote sensing you can ever come across. Don't mind the grammar that is there. What I'm saying in essence, in just a sentence, is that anytime you hear the word remote sensing means the art or science or even the ability for you to be able to capture or to obtain an information of a specific, or it might not even be specific, or for you to be able to capture any information related to it, that it can be a feature, an object, a scene, a location, or anywhere without you making a physical contact. That is remote sensing. So what I'm saying is that let's assume I want to measure the temperature of Pacific Ocean. For an instance, I want to know what is the temperature currently of the Pacific Ocean. So what is remote sensing in that? How is remote sensing related to this? That I don't have to go to Pacific Ocean to actually use my tool to measure the temperature range. So through the technology of remote sensing, I can be at my comfort zone, I can be inside my room, inside my house, and know what the temperature of Pacific Ocean is actually saying. I don't know if that is clear enough. That in my own comfort zone, as I'm here seated right here, I can actually know what is actually happening in the United States. As I'm here at the moment, as I'm seated here at the moment, I can actually know what is happening in one particular country, a future in one particular country, or a scene, an object, or anything. I can actually know what is actually going. That is what remote sensing is. I don't know if that is clear. So it's just the science and art of obtaining an information, whatsoever the information you are willing to actually obtain from that particular area or that particular study that you are trying to make, without what making physical contact. So you have to be very careful about the keywords. One of the keywords that is here that must not be left out while you are trying to define remote sensing is that without making physical contact. If you are making physical contact to get an information, that is no more remote sensing. Hello? If you are making physical contact that you have to touch the object, you have to, get there, that is no more remote sensing. Remote sensing is that I am obtaining an information, I am getting an information of particular place, of a future, of something, without my physical presence in that place. I don't know if that is clear. If that is clear, let me just give a reaction to that. I hope you guys can still hear me. Just don't unmute, just type it, just drop your comment, please. I hope you guys can still hear me. I'm not seeing, can you guys still hear me? Okay, thank you very much. Thank you very much. Thank you very much. So, I said that it involved detecting and measuring electromagnetic radiation reflected or emitted from the Earth's surface, typically using sensors mounted on platforms such as satellites, aircraft, and drones. I will explain that as we proceed. This information is then processed and analyzed to understand and monitor the physical characteristics and changes on the Earth's surface. Don't worry, you'll get the better idea of what I'm actually saying as we proceed. So now here is how it works. So the question is that this data, how is it possible, or how does it make sense that I can be able to get the information of a particular place? I can be able to get the information of an object, no matter how sensitive that information is. How is it possible that I can be able to derive or obtain that information without my physical presence there? And here is actually how it works. Remote sensing works by detecting electromagnetic radiation. Now, for the physics students, I really don't want to go into the technicality part. I'm just trying to bring the overview. I don't want to start talking about light and all like that. I'm just trying to bring, to come up with just to scratch the surface and to give context to what I'm saying. Remote sensing works by detecting the electromagnetic radiation, EMR, that is reflected or emitted from the Earth's surface. The primary source of this energy is sun for passive system, although some systems generate their own energy system. Now, what am I trying to say in this slide that you are seeing? This thing that is actually oh, sorry, hold on. Okay, now, how does this remote sensing work? Now, I'm trying to, give a better context. So this is how it works. Just flow with me here. There are let me just say 7 basic process in which the data that we use, that data that we'll start using, or the data that we're about to download now, there are three technical processes or three backend processes that actually happens that make that data the data that we are trying to use. So here is how it begins. Generally speaking, in remote sensing, there are two types of remote sensing, but let me speak to the first one, which is what we know as passive remote sensing. We have the sun. That sun you are seeing is one of the tools we use in remote sensing. So that sun you are seeing, it does something called emission. It emits an energy. This sun, this particular sun, I'm not talking about any other sun, this particular sun you are seeing, it emits an energy. There is an energy that is coming. There is an energy that sun actually emits. So that energy comes from the sun and it hits a particular surface on the Earth surface. Now, look at that image that is actually showing on your screen. You discover that I say, number one, we have the energy source. So you see that there is an arrow, all these yellow arrow that you're actually seeing now, that is more like a description of the emitted energy that sun is bringing out. Now, that sun hits the Earth surface. That energy hits the Earth surface. So no matter the Earth surface, no matter what is actually upon that Earth surface, it can be water, it can be mountain, it can be vegetation, it can be forest, or any particular thing the Earth surface hits. So there is an interaction that happens between the emitted energy and that particular surface that energy actually hits. I don't know if it's making sense to you. See, just as I'm speaking, just flow along with that diagram. This diagram is actually the best representation of how remote sensing works. So there is a sun, which is actually our major source of how this data is actually being generated. There is an energy, which is the sun. The energy, the sun emits an energy. So this sun now hits this energy that is emitted by the sun hits the Earth surface, no matter the Earth surface and all. So here is now what happened. Now, when the energy hits the Earth surface, there is something we call, in fact, there is three processes that happen. I'm avoiding to use technical words just for the sake of everybody to be carried along, especially some people who are actually new to this thing. So I'm really avoiding to use technical words. So basically what I'm saying is that once that energy hits the Earth surface, there are three processes that happen. The first one, we call it transmission. No, we call it interaction. There is an interaction that happens. Secondly, we call it absorption. There is an absorption that happens. And lastly, we call it reflection. Take note, an interaction happens between the emitted energy and the features that is upon the Earth surface. Please, just don't. I really hope that I don't lose anyone. See, it's very simple. Don't get it twisted. Sun emit an energy. Once it reaches the Earth surface, there are three processes that happen. That energy interacts with whatsoever features that it hit on the Earth surface, number one. Number two, there is something called an absorption that actually happens upon that Earth surface after eating it. And lastly, there's something called reflection. So the interaction happens that, okay, this sun actually hits the particular surface. Something is happening. There's an interaction that is actually happening. Then you have to now understand that it is not all the... So let's assume, okay, let's use mathematical expression now. If 30,000, okay, let's say 100 energy is actually hitting the Earth surface, coming from the Earth surface, hitting the Earth surface. So out of that 100, note that immediately hits the Earth surface, it will not be 100% entirely again, because there is even an interaction with the atmosphere. I just don't want to go there. As that energy is actually coming down, there is also an interaction with the atmosphere. There is something we call scattering, interaction, and so on and so forth like that, but I don't want to go into that. I'm only concerned about the Earth surface. So there is an interaction that actually happens when that particular energy, that 100, when it hits that surface. So it might be maybe like 90% that will later hit the Earth surface. Now, have the understanding that in the process of interaction within that 90 and that particular feature or the Earth surface or that particular feature will also absorb its own energy. Please just flow with me. There will always be an absorption that happens. So it means that in that 90%, yeah, that depending on that particular future. So 30% might be taken away, 20% might be taken away. I'm just trying to explain this in a mathematical concept. 10% might be taken away, 50% might be taken away. It depends on the atmosphere. Then lastly, the process that now takes place is called the reflected energy or the reflectance energy. So it means that the remaining energy that is left after the interaction and the absorption, it means that every object you see upon the Earth's surface that the energy emitted from the sun hits, there is always a reflected energy that reflects back again. I don't know if that makes sense. So look at that image again. This image on your screen. You can see the arrow from the sun hitting the Earth's surface. Then you discover that there is another arrow again, or more like a line that actually goes back up again. That is what we call reflectance. So this line that you are seeing, that you see that line is coming directly from the Earth's surface, is going back. That is what we call the reflectance energy. Take note of that. So it's basically simple. It's simple. Like it's simple. In fact, as I said, it's actually in seven processes, but I'm now trying to shorten it down for you into 3 processes. The emitted energy, number 1. There is, after their emitted energy hits the Earth's surface, there is an interaction that actually happens. There is an absorption that happens, and there is actually there's actually an energy that is being reflected back. Does that actually make sense? Now, it is now this reflected energy. It is this reflected substance that it reflects back that our remote sensing platform actually records. Please, you can just try to meditate on it. For instance, let's take for instance our physical instrument. Just like what kind of instrument can I use? For instance, okay, let's say thermometer for an instance. Let's say thermometer for an instance. This thermometer, I don't know the name of that thermometer, but the common ones they use in the hospital, you will discover that there is one ion at the tip of that particular thermometer. So let's take that ion more like a sensor. So what happened is that immediately they put that thermometer under your armpit. What they are doing is that your armpit is more like a so you can just picture it as more like a reflected energy that is sensing information to the sensor. So the work of the sensor is that it records what is being reflected back and it records those information. So it is the processing of those reflected energy that gives us this raster data that we are talking about, or this special data we are talking about. Does that even make sense to you at all? Please let me see your comments. I don't know if that makes sense to you, or if you have any other question.
Yes, but actually it is not clear, sir. Can you take it again?
Sorry, what did you say? Sorry, you were saying something. Can you type, please?
Okay, sir. Let me type.
Okay, someone said it's still listening or observing according to the sensor, even when it is visual. Even when it is visual, a type of listening, there is difference between listening and hearing. Sorry, I don't know what Brian, what do you mean by listening and hearing? And it is not always listening because it's used light intensity value. So better can it dictate? Okay, Brian, please, if you can actually explain better, okay, I was answering the okay. I get now. Okay, you're asking more example. Okay, what other example can I use? Just think of your physical, think of your physical, what's it called? Your physical equipment you use. Maybe some of you who are in geology, for instance. Is geology the best example to use here? Any aspect you are working, I believe that especially those of you who work in the technicality, again, the technical aspect, there will always be an instrument you guys actually use. There will always be an instrument. And one of the things that you guys do is that you guys go to the field. You go to the field, right? And maybe you have to place that particular instrument upon the earth surface just to read a number. Am I right about that? So you are looking for a value to actually record, blah, blah, blah. So that is similar to how it works. So what is happening in that process? How you were able to get that value that you recorded was that there was an interaction that was happening. There was a transmission in energy sent to the sensor that is inside your equipment. I don't know, maybe you get. Let's assume your instrument is something that you have to place on the ground, or you have to dig into the ground before you can take the recordings. So what happens is that immediately you stick that particular instrument on the ground, inside the ground, I mean. So there is an interaction. That earth surface is emitting something. So the sensor that is inside the equipment to struck into the ground is now recording those particular energy that particular surface, that particular place that you struck, that particular thing that is emitting is the one. It is now, that sensor is now recording those particular information. That is why you can be able to see those values that those particular thing is actually generating. I don't know if that is still clear. I don't know if that is still clear. Yeah, thank you, Bram. I think I'm still actually going to go. I really don't want to go into the technicality, because normal we're supposed to start talking about the electromagnetic spectrum, but for the sake of those who are not even who are not in science aspects, it might really be difficult for them to actually understand the whole concept. Mr. Sulaiman said, example, theodolite instrument, maybe something like that. Though I've not actually used a theodolite instrument before. I've not actually used it before, but the best way I think I can explain this is that just think of it like an instrument you guys take to the field to record a particular information. So I'm not telling you that how you're able to get those information is that, especially the instrument that actually has to do with you actually mounting it on the ground, like maybe digging it, you want to collect I really don't know. I think the geology student amongst us should be able to understand what I'm actually saying. So how you're able to get those recordings that you recorded is that there is an interaction that happened between that particular thing you are measuring and the sensor that is inside that equipment. That is how you're able to get the reading that is there. That is exactly how remote sensing works. From the sun, which is actually our major source, hits the particular target or hits the particular surface, then there is a reflected energy that bounces back. It bounces back. Then that energy that bounces back, it is what all our platform, all the remote sensing platform, which we are going to look into shortly, that actually records. I don't know if you get that actually records. For instance, the satellite, there is a sensor that is mounted upon the satellite. So it is this reflected energy that the sensor mounted upon the satellite records to give us the data that we are using. That is just simple. Don't think of it too much. That is just very simple. As I said, there is actually a lot, from what I even see. You see that I wrote energy source, atmosphere interaction, recording of energy transmission, processing and analyzing application. Those are actually the 7 processes of how the data are actually being getting, but I really don't want to go into the all technical details. So, okay, I even put more like a technical details here. I said electromagnetic spectrum in remote sensing. I said the electromagnetic encompasses all wavelength of electromagnetic radiation, from gamma ray to radio wave to remote sensing. Remote sensing primarily utilizes the following region. So if you are a physics student, or peradventure you've done physics before, I believe that you should know what electromagnetic is. So electromagnetic spectrum is more like how should I describe it? It's more like a broad band where light is being captured in different wavelengths. I don't know, maybe you understand. So the usefulness of this electromagnetic spectrum is that it helps us detect informations or light. That now I think if you are a good student, or if you are someone who actually catches something, you automatically sense that this remote sensing has to do with light. I don't know if you really follow my explanation. Automatically, you should understand that remote sensing has to do with light. So that is where the electromagnetic spectrum comes in. So those lights that are being reflected, that are being emitted, reflected back, electromagnetic now help us capture different information across these wavelengths. So we have various of them, starting from the visible region, near infrared region, the wavelength region, the thermal region, microwave, and so on and so forth like that. So the work of this electromagnetic spectrum is help us capture information across all these wavelengths, and that is exactly what we utilize in remote sensing. I think this might actually make sense when we start our practical section, when we have to do with downloading different bands, when we start making use of different bands. Band 1, you'll be hearing something like band 1, you'll be hearing something like near infrared, the red band, the green band, and so on. I think when we start our practical, I believe that it's going to make a lot of sense. So I said something that is very important. Now, I was explaining something earlier that in the course of the interaction between the emitted energy and the reflected energy, that there is something called an interaction that happens and also a absorption that happens. Now, you have to take note of something, that the reflected energy is totally dependent on the material, or what's the right word to use like this? It's totally dependent on the material or the features that light, the emitted energy, actually interacts with. So here is what I'm saying. The reflected energy of water will be different from the reflected energy of a tree. So it means that when light bounce on water, there will always be more of an absorption. Does that make sense to you? That energy that is being emitted from the sun, that energy that light that comes from the sun, if it hits water, there will always be more absorption. So in that kind of case, less energy is reflected back. Just like the mathematical expression that I was trying to explain to you. So let's assume 100% light actually hits water. There will always be at least, I'm just saying, this is just, I'm not saying this is it, I'm just citing an example. When it hits water, there might be like 90% absorption, while it might only be that 10% will actually be reflected back. So compared to when that energy, that 100% actually hits maybe a bare ground, a tile road, that kind of way, in fact, you can even say that maybe it can only be maybe 1% out of that 100% that will only be absorbed. Meanwhile, 99% can actually be reflected back. So I said that different objects emit or reflect energy differently across the electromagnetic spectrum. Each surface, features like vegetation, water, soil, building, interact uniquely with electromagnetic radiation in different wavelengths. I mean, these are all physics terms. That's why I'm trying to caution myself not to actually go deep into them, so that I will not get confused. So basically what I'm saying is that, you see, this region, these bands like this, visible, near infrared, and so and so and so like this, the way the electromagnetic is designed is that there is a feature we reflect more or we interact more in one of these particular region. So for an instance, in maybe the red band, which falls under the visible region, the visible light, if the emitted energy hits a vegetation or a forest, if it hits a forest, now when the electromagnetic now comes into play, is that in the visible region, especially the red band, there will be less reflection. It might not be able to detect it, but once it moves from that visible region to maybe something like a near infrared, it picks it immediately. And this is where analysis like vegetation indexes actually make sense to you. Don't worry, I think it's one of the analysis that we'll be doing, vegetation indexes. I think you can be able to get what I'm saying. That one of the way that, okay, practical example is that you might want to be asking, especially for those of us in agriculture, that how is it possible for us to be able to know that this plant is not actually doing okay before time? Remember that I think in our first class, I explained that it's possible through remote sensing, through GIS, for us to be able to know the health status of a plant even before it actually happens, even before maybe a disease actually breaks out. Now, you can now try retracing it back that this is exactly like this is the pain point exactly about how that particular thing actually comes onto play. That these electromagnetic spectrum are designed in a way that they can detect even the smallest changes. There's a region that can pick the smallest changes that is not visible to the eyes. So the visible region is just speaking more of the RGB, the red, green, the one that we can see, the visible one that we can see. But immediately you start moving from the visible band, the visible region, now to the near infrared. Now our eyes can no longer see those particular information, see those particular thing again. Shortwave infrared, your eyes can no longer see them again. The thermal region, these our eyes can no longer see them. So that is where the electromagnetic and sensor actually, correlate. That in all this region, there are these regions or this light or this particular wavelength, they are sensitive to changes per region or per time. I don't really know how to put that. That in near infrared, a slightest change in a vegetation nitrogen level or chlorophyll level can be detected, can be known. I don't know if that actually makes sense to us at all. I'm really trying to caution myself not to actually go into the real, like the technicality aspect from it. Reflection equals to bouncing energy. The sunshine on the earth and some energy bounce back on the sensor. Emission equals to giving off energy. Thank you. Earth gives warmth and gives off its own heat energy, and so on and so forth. Please, I need your call. Just give me a thumbs up or a comment if you're actually really catching what I'm saying. I mean, I'm just trying to, as I said, I don't really want to use too much of technicality in this thing. I'm just trying to carry everybody along and at the same time not to confuse anyone. Please, I do not think there is anyone here that is not of science inclined. So just go technical and use all required terminologies to explain for better understanding. I agree with you, but at the same time, you have to understand that there are a lot of people also who did not have background to these things. So that's why I'm just being conscious. But however, I really hope that I'm able to carry everybody along. But let's just proceed. And I believe that you're able to get the full understanding, the full scope. Because of this variation, the reflectance pattern of an object across multiple bands can be plotted as a graph called spectral signature. So there's something we call spectral signature in remote sensing. And what does this spectral signature do? This is typically an example of how spectral signature is. Look at this image you are seeing on your screen. Look at this image you are seeing, this graph, something that looks like graph that you are seeing. Now, this is what we call spectral signature. Now, what is this actually telling us? If you look at the down part of this our graph here, you see 0.5, 0.7, blah, 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 so on, 2.5, blah, 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 and so on and so forth like that. Now, those are indications of the various, of the various regions in the electromagnetic spectrum that we have. So what I'm saying is that, look at this one that I'm saying, that diagram here, this visible, near infrared, shortwave infrared, thermal infrared, and so on. So you can see here that it's been stated here that anytime you have 0.4 to 0.77, I don't even know, is this micrometer or something like that? Anytime you have that, it means that is where the visible region actually ends, though it differs sometimes. That anytime you have from 0.7 to 1.7, now you have moved from visible region now to near infrared. That anytime you have 1.3 to 3, now you are now in the shortwave infrared. Anytime you have from thermal infrared 3.33 to 14, now you are now in the thermal infrared, and so on and so forth. That is exactly what this graph is actually showing us down here. So now here is what now happened. Once this sensor capture those information, once we use our tool to actually there's something we call, is this spectrometer like this? I think spectrometer or something like that in remote sensing. It's more like a handy tool. So you can actually just place it upon that particular feature or that particular object. You just place it and it reads the reflected energy back. So once you now bring it into a GIS environment, you can be able to plot something like this. And the interpretation of what you are seeing here is this. Now, look at water, for instance. Can you see water? This water is blue, right? You will discover that there is a peak in water. There is a particular place that water actually reached, that there was a peak, and you discover that as time goes on, it begins to decline. So here is what is happening. So it's automatically telling us, what it means is that it's automatically telling us that in this particular region, perhaps in 0.5, and if you actually understand how electromagnetic work, or if you have a concept, you note that 0.5 is sometimes around, is most time the blue band, the blue band, or the blue region band. So it's telling us that band, water is more sensitive. So it was able to detect water in that particular band. So when it now begins to shift from 0.6, 0.7, 0.so, you see that there was a decline, meaning that the rest of the region did not have the capacity again to capture those information. That where water is only sensitive, or where you can be able to pick water, is actually between that particular region, that is only sensitive in that particular region. Another example is green vegetation. We will discover something that in green vegetation, as at maybe 0.3, 0.2, it was still low. But you will discover that when it automatically gets to maybe around, let's say, 0.6 or something like that, you discover that there was high incline. And you discover that this trend continues until 1.3. Now, if you look into this particular thing I show you, that for anything ranging from 0.7 to 1.3, that is near infrared region. So automatically, it means that from this 0.7 to this particular place, this is automatically a near infrared region. So it automatically implies that vegetation are more sensitive in the region of the near infrared. I don't know if that makes sense to you. That immediately you start getting away from the visible region, and now we are moving into the near infrared region. In that kind of way, it is vegetation like in that particular region, you can be able to capture information more. In the near infrared. So one of the advantage, or one of the importance of this, is that if you are working on, I think the best example I can also use is vegetation indices. Vegetation indices, where we are still going to do the analysis. Now, these are the formations that some of these scientists actually use to be able to derive something we call the vegetation indices, the mathematical expression of the vegetation indices they use. So once you are able to know the region at which these features actually relate with, automatically gives you an idea of the kind of band you are supposed to use. That's just the whole idea. Once you can be able to know that, vegetation is more sensitive in this particular region, the near infrared, the red edge region, automatically gives you an idea that, next time if I'm doing my project, I should majorly focus my attention on this band. I don't know if that actually makes sense to you. Same thing as soil. You discover that there was a high surge. There's actually a tradition or something like that with soil. So it gives us an understanding. The meaning is that soil is sensitive even in the visible region. Soil is sensitive even in the near infrared, even is sensitive in the short wave, even though it's sensitive in the thermal region. That is automatically what that soil you are seeing is. You discover that it's more like a projection is going up. So that gives us an idea that soil, that anytime we are actually doing something related to soil analysis or something like that, visible bands are okay to use. Near infrared, the near infrared band is okay to use. The thermal band is okay to use. The shortwave infrared band is okay to use, and so on and so forth. I don't know if that actually makes sense. I got lost when you talked about the red band, infrared. don't worry, there is analysis that we're going to be doing that all these things I'm actually saying will still actually make sense. And that is why I'm even bringing it up now, so that once we get to the analysis, you will not feel lost completely. So, but if you don't really get what I'm saying, just be patient until we start getting into, I think next week by God's grace, we'll be entering into full analysis, no much talking, and you can be able to understand all these particular bands, all these particular terminologies I'm actually using. So is there another thing again? Well understood and makes more sense. Thank you very much. Please, I do not think. Okay, let me check here again. I'm just trying to check the comment section to see if I'm not missing anything. I hope you guys are still with me. Are you guys still with me, please? Can I move on? Please, I need you guys comment. Can I move on? Okay, all right. Thank you. Thank you very much. So I was saying that there are two types of remote sensing earlier. There is something we call passive remote sensing and active remote sensing. So what is the difference between active remote sensing and passive remote sensing and active remote sensing? Let me just summarize it for you so that we'll not start, or let me see if I can read what is here. I say passive remote sensing relies on natural energy source, mainly sun dictate the electromagnetic, so on and so forth. Now, not to confuse you or not to waste time, the difference between passive and active remote sensing is that passive remote sensing make use of sun as the major source of energy, while active remote sensing generates their own source, meaning that they don't use sun. Simple as ABC. There are different, there are a lot of differences, but what summarize all those differences, or the major points that summarize the differences between a passive remote sensing and an active remote sensing, is that in passive remote sensing, our major source, as I explained to you, is what? The sun. While in active remote sensing, instead of them depending on the sun, themselves, they embodied or they carry their own energy. So automatically, as a student, you should be able to give a context that another differences between these two is that in active remote sensing, you don't depend on sun. Does that make sense? So it means that at night, passive remote sensing might be useless or might not be needed. Does this make sense? That for night, that there is no sun, it means that if you are relying on passive remote sensing, it means that there is nothing much you cannot do. But however, if you are operating on an active remote sensing tool or platform, it means that even at night, even in rainy season, even in any kind of weather condition, you are relaxed that it will still give you the results you want. Does that make sense? That's just the major difference between passive. The whole thing I actually write, the whole thing I pen down here, blah, 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 this and this, that is just. So how does active remote sensing work? Now, what I explained initially was passive remote sensing, that you need the sun to the earth surface, then the earth surface to the sensor that actually records the information. So in active remote sensing, how does active remote sensing works? Active remote sensing works by, it's just all needed in active remote sensing is just the tool, it's just the platform. An example, LiDAR. I believe that some of you will know LiDAR very well. Anytime LiDAR is operating, LiDAR does not need sun. Why? Because LiDAR in itself carries its own energy, carries its own source of energy. And what is the source of energy of LiDAR? It is what we call what's even is it LiDAR, or what is even the major source, or how am I supposed to put this? I think it's just major. I personally call it point cloud. LISA, I think some people call it LISA. Yeah, thank you very much. Yeah, Brian, LISA. So I don't know, you should have seen how LISA looks like now. LISA. laser is just this tiny, I'm just giving a basic, how I put it, I'm just trying to give a basic clear example. Laser is just more like a point cloud, more like a point something that pointed from that instrument to that particular surface, that particular object. So it just points, like just generates this point or this laser, this thing, this visible or invisible or whatsoever thing to that particular, directly to that particular object. That is why it is easier for you to be able to measure the distance automatically using LiDAR. It is more easier for you to be able to, I think laser can be, well, don't let me say what I'm not sure of, Sha. But my point is that is why, because of the technology of the point it used or the laser it used, that is why it is easier for things like 3D to be made possible. That is why I'm trying not to go outside of the scope. Now, how 3D was able to work. Now, this should give you an automatically understanding that 3D might not be possible with the aid of passive remote sensing, but the aid of what? Of active remote sensing. And a clear example of perhaps maybe you've come across a 3D image before. How that 3D image actually comes into play is actually through, most time, through the technology of this laser or this LiDAR of this LiDAR sensor or this LiDAR tool. Sure, you understand? So it drops a point, and I said that I didn't prepare for it, but I said I wanted to show how that actually works. But just for knowledge sake, it makes use of point cloud or laser, whatsoever thing you want to call it. So it just automatically points, like, I don't even know the right word to use. It just brings out all those points. It just point out all those points to all those particular features you are trying to measure automatically. So in that kind of case, you don't need sun. Remember that in passive remote sensing, what you depend on is the reflected energy. And if there is no sun, if there is not emitted energy, there might not be a reflected energy. Though that is not actually the case sometimes, because even at night, the earth still emits sometimes. But I'm just saying that sometimes in passive remote sensing, you need light, you need something, you need an energy to reflect back, because it's that energy that sensor mounted upon satellite or whatsoever platform you are using that is those particular reflected, is that particular reflected energy that those sensor actually depends on to be able to record those particular information. So I'm not saying that in active remote sensing that process is not needed. The process of active remote sensing is just two process. To me, it's just two process. It send out its own energy, the laser or the pointer is send it out, and the sensor that is being installed in that particular LiDAR or that particular platform you are using for the active remote sensing, it records back the reflected energy. So that point cloud, that point thing, that laser or that point that actually transmit, that actually went out, there is a sensor too inside that particular technology you are using, maybe LiDAR for instance, that you are using, that also automatically record the information that is being captured through that laser or through that point cloud. Okay, Brian has helped us here. He said LiDAR equals to shoot laser. Thank you very much. Maybe that was even what I was looking for. It shoot a laser. It shoot a laser. It automatically measures it measures the bounce energy that actually comes back from that laser that it shoots. Then it calculates the distance, and that is how we can be able to generate something like 3D map. Let's see if maybe just a play around, maybe you can actually look about how this 3D actually works. So I believe that is clear enough. The difference between a passive and active remote sensing. Don't get confused. It's simple. Passive remote sensing has to do with sun, meaning that you need sun. You need an emitted energy and a reflected energy. So you need in passive remote sensing, the major thing that we need is sun. But in active remote sensing, they carry their own sun. Just put it that way. That active remote sensing carry their own sun, though it is not sun, no, but I'm just putting that in context that active remote sensing carry their own energy, so they don't need sun. They have what they have to emit themselves. So in the case of LiDAR, it emits laser. I think that's even the best word to use. In passive remote sensing, the sun emits its own energy, but in active remote sensing, for instance, e.g. LiDAR, it emits its own energy using the laser technology to record information. Simple as ABC. Is that clear? Someone said satellite use both active and passive remote sensing, and laser use only active remote sensing. Yeah, of course. Satellite use active and passive remote sensing. I think I'm still going there. So there is another technology or satellite called radar. Radar is also, am I right? Yeah, I'm correct now. Radar is called ranging. Oh, Jesus, radar. Ranging and something. Can someone let me drop the meaning of radar? It actually skipped my head now. The full meaning of radar is it should be ranging and detecting something. Oh, sorry, radio detection and ranging. Thank you very much, Mr. Medford. Radio detection and ranging. Thank you very much. Thank you very much. So that's the meaning of radar. So it's also a satellite. It's also a satellite, but for this course for now, I don't think we'll be making use of radar or SAR. I don't think, no, we are not making use of it. And one of the things you have to understand is that this data or this platform or this type of remote sensing, sometimes it influences or it automatically there is a how will I put this? They generate different kind of data. Should I put it that way? Yeah, they generate different kind of data. SAT data or active remote sensing data is different from the data that a passive remote sensing will generate for you. The radar data is different from optical data. The data that all these normal satellite, our passive remote sensing generates, we call it optical data, optical remote sensing. So optical remote sensing data is different from SAR. The radar I'm talking about, the data it generates is what we call SAR. SAR. Can someone also put the meaning of SAR? SAR image, SAR. I'm waiting. SAR. That's the name of the data that radar actually generates. No comment. Let me just go ahead. Thank you very much. Synthetic aperture radar. That's the name of SAR imagery. So it's different from an optical imagery. They serve their different purposes. Sometimes you can even match both SAR and you can match both active and passive data. You can even match them together actually sometimes. You can match them together sometimes. I've done that before, depending on the project you are doing, or maybe you are trying to do research. So, so basically that's just all about active and passive remote sensing. So I state here that these are the major differences between passive and active remote sensing. The energy source, which I've actually explained that passive uses its own energy, which is sun, while active generates its own. Sensor function, the sensor only receives reflected or emitted radiation. I said that in passive, the sensor only receives the reflected energy or the emitted energy that bounces back. While in active, the sensor sends out energy and measure the reflected signal. Dependent on sunlight, I said it that, of course, before passive can work, it requires sunlight to capture reflected data. While inactive does not depend on sunlight. You don't need sunlight to actually use a active remote sensing, for instance, LiDAR. Weather condition can be affected by cloud and atmosphere condition. Don't worry, you see, this particular statement can be affected by cloud and atmosphere. In very short, when we start downloading data now, you totally understand what I actually mean by that. That sometimes this passive remote sensing that we were using, sometimes to get it can be very frustrating. Don't worry, we are getting into it, and you can actually see yourself. Can operate in most weather conditions, even at night. Yeah, nights, midnight, it works both day and night. Yeah, thank you. Okay. Yeah, Mr. Medford has already said it. He said it works both day and night, can see through clouds, can detect things like water, building, even it can detect the most smallest thing, most tiniest thing. It has the ability to detect it. That is active, that's LiDAR, especially LiDAR. Example is Landsat, Sentinel, optical imagery. An example of active is radar, which is SAR, and the LiDAR. So, can I move? Is there any question? Is there any question? What are the example of body object that uses? What are the example body that uses? What are the example of body or object that uses passive and active? I don't really understand that question. What do you mean by body or object? Are you talking about the tools or the what's it called? Please, still in the spirit of this your explanation, how does this remote sensing apply to disease outbreak? Don't worry, you will get there. Don't let me answer your question. I want to go to the practical, you understand? Now, okay, one thing you have to able to now what I've been explaining since morning. I think let me actually bring that clarity. This active remote sensing, passive remote sensing that I've been talking about, majorly is categorized under how we get our raster data. Take note of that. All the raster data we use or will be using, it actually, what I've been explaining mostly since morning is actually falls under it. So remember that we have vector data, we have raster data. So don't get confused. There is something we call vector analysis and there's something we call raster analysis. So your question, okay, sorry if I didn't pronounce your name well. So you just have to be patient so that your question to me looks like a vector analysis actually that you're actually asking, but I will get there. You still understand, or you still understand better. So don't get it confused. What majorly, as I said, majorly what I've been explaining this morning is how this raster data that we make use of, how they actually come about, how they are actually being generated. So please be patient, Mr. Chijos. I don't know your name. I didn't get your pronunciation well. So 3 platforms of remote sensing. I think I really need to move now. Time is fast spent. So we have 3 major platforms of remote sensing. Number 1, we have the ground-based platform, we have the airborne platform, and we have the space-borne platform. What are the differences between these 3 platforms? It is altitude. That's just the simple term, but don't go and write that. Don't go and write that maybe if you are doing exam. But I'm just trying to tell you that the difference between the 3 platforms of remote sensing, which is the ground-based, the airborne, and the spaceborne, is the differences in the altitude. Majorly is the differences in the altitude. So in ground-based, that actually talks about most of your physical equipment, your tools, okay, I think I cited example here, your weather station. Now, for instance, weather station, you have to cite all your equipment, your rain gauge, your so on and so forth. You have to mount it upon the ground, right? That is why we call it ground-based. So sometimes we also classify this as remote sensing tool as well. We always say it is also part of remote sensing tools. I mean, ground radar system and so on. So that is ground-based platform or ground-based platform of sensor. Then we move to airborne. Airborne sensors are mounted on aircraft, sometimes UAV, aircraft or UAV. It provides high-resolution data over specific area and is commonly used for mapping, agriculture, and so on. So what I'm saying in essence is that once you move from ground-based, meaning that the equipment that is being installed on the ground, the next thing that you will see again is called the airborne, meaning that these platforms or this sensor only operates in the air. Is that the right word to use? They only operate within certain range of an altitude. Yeah, I think that should be the best way to put it. Meaning that they cannot go beyond some certain altitude. And that is what differentiates airborne from spaceborne. Now, the difference between spaceborne and airborne, they are both remote sensing platform, but the only difference is that when we talk about spaceborne, majorly we are talking about satellite. And why is the difference is that Satellites are launched thousands of kilometers away. In fact, some are even launched maybe 36,000 kilometers away. The satellites that we are most familiar, most common with, satellite Landsat, so on and so forth. Those platforms, they are launched thousands of kilometers away. Thousands of kilometers away. So why the spaceborne, there is, for instance, aircraft cannot reach the altitude of where satellite is. Drone, UAV cannot reach the altitude of where satellite is. That is why it is being differentiated that we have airborne and spaceborne. So anytime you hear airborne platform, just think of aircraft, UAV, which is our drone. So I mean, there is a limit at which all this one can actually reach, compared to a satellite that is actually being launched to the space. It's not launched even to atmosphere. It's not what we see with our eyes. I mean, you cannot look up and tell me that you have seen satellites. It's launched far away. So that's just the major difference between airborne and spaceborne. Does that make sense? Does that make sense? Please, I need a thumbs up if I can proceed. So those are the major three platforms you have: the ground-based, the the airborne, and the spaceborne. Anytime we talk about the spaceborne, just think of satellite. That's basically what we mean when we talk about spaceborne platform, satellite. And there are various types of satellite, different kinds of satellites. I don't know if you're going to talk about that, but I have to understand that major type of satellites, the Landsat, and what you have to know again is that these satellites are actually made, or they actually their configuration differs depending on their objective or their mission. So we have hundreds or thousands of satellites up there. Here you get, but you have to be able to understand that all of these satellites do not give the same information. Like, they are of various purposes. There are satellites that are launched that their purpose is just for maybe weather monitoring. There is a satellite launch that its purpose is just for land cover or land mapping or land coverage or something like that. There are satellites that is for surveillance. There are satellites that what other purpose? Various purposes that you can actually think of. So depends on the mission. Though, aside that, there are actually various differences between, various attributes of this data. For instance, Landsat satellites is different from Sentinel Landsat, Sentinel data. Sentinel satellite, or how you want to put it, they are bit different, even though they still have the same purposes, but their attributes are actually different. So when we move to the analysis part, I think I will explain that more better. So we have type of image resolution. As I said earlier, please take note of that basically what I've been saying this morning is majorly pertaining to raster dataset. So when you have your raster dataset, now have the consciousness or have the understanding that the data in your hand, the data you have, contain 4 type of resolution. I don't know if that is even the how to put it right, but I have the understanding that there are 4 different resolution in that data that is your hand, that raster data that is your hand. I have the consciousness that this data with me, this data that I'm seeing, contain 4 type of resolution in remote sensing. Number 1, we have something we call the spatial resolution. Please look at your screen and know the spelling. Maybe if I'm not even pronouncing it well, please take note of the spellings. So spatial resolution, we have something called the spectral resolution, we have something we call the temporal resolution, and we have something called the radiometric resolution. Take note of that. Now, what is spatial resolution? In fact, if you attended the first class, I think I tried to explain some of this terminology, some of this resolution to us. So what is spatial resolution? Now, this is where things now start getting more technical, and I need to explain this technicality for you, because if you don't get this technicality, this thing I'm about to explain, it will affect you when you start downloading your own personal data. Because you have to be able to understand that your objective or what you are trying to do, the analysis you are trying to do is totally dependent on the data, the availability of the data or the data you have. So it's possible for you to go and download the data, and at the end of the day, the data will not be useful for your objective again. So how will you be able to know which data am I supposed to use? Which data is right for me to use? It's totally not dependent on these 4 resolutions that I'm trying that I want to explain now. You really have to pay attention to it, that if they give you data, from you looking at the data, from the metadata of the data, you can be able to know, okay, this and this. And for some of you who are actually done with the assignment of these 3, there is one technical question that I actually put in there's one technical question I put in your assignment. And the major reason why I put that technical question there is just to test your understanding about if you really understand these 4 types of resolution. It's very, very important. I know some of you just went to AI to give you the answer and you paste it there for me. Don't worry. And mind you, starting from next week class, I did not reject any assignment. Yeah, that reminds me, there is one particular person I mistakenly rejected his assignment. Please, if you are that person, kindly resubmit the assignment again. I will approve it. It was a mistake from my hand here. But take note that from next week, because from next week is now more practical, and what you guys will be submitting is more of what you've done, what you are doing. So if you are not doing what you are supposed to do, your assignment will be rejected starting from next week. This 1, 2, 3 week, I did not reject any assignment. I approved anything. Even those of you that went to copy the whole prompt of AI together with the question and the answer, you copy together. Well done. Good luck to you. So now let's get right into it. So what I'm trying to say, what I'm trying to explain to you now is that please flow along with this 4 type of resolution, because they will greatly influence the data that you will be downloading or you will be using. Number 1, we have the spatial resolution. What is the spatial resolution? What does it refer to? Spatial resolution refers to the size of the smallest object that can be detected on the ground. In digital imagery, this corresponds to the pixel size. It is defined as the area on the Earth's surface over which an independent measurement can be made by the sensor. Small pixel equals to final details, which equals to small details. Now, here's the grammar. When we talk about spatial resolution, think of it of a size. Now, I think I explained this thing. I took my time to explain this in first class. Now, let's use our phone camera for an instance. Let's make it use for an instance. I was trying to explain something to us in that first class, that if you look at your phone camera, you always see something like the zoom ratio or the zoom level. I don't know how you guys call it, the zoom level or the zoom ratio. You always see something like 1, 2. So it means that you can zoom to 1, you can zoom to 2, you can zoom to 3. Now, the question is that what is the difference between this zoom capacity, this zoom level? What is telling us that the details that 1, if you put it in 1, the details that it will capture for you, the size it will capture for you is totally different from the size that 2 will capture for you. It's totally different from when you put it with 3 zoom or 3 ratio that it will give you. Does that make sense? Now, this thing I'm saying is a pure practical something. If you bring out your phone and you want to take a picture and you put it as 1, you set the ratio as 1. Are you flowing with me? Screen is blur. Is my screen blur? Please, is my screen blur? Someone is saying my screen is blur. I don't know. I saw someone said no. Now YouTube people, I think I saw this from YouTube people. Please verify again, YouTube people. Is my screen blur? Please let me know. But the YouTube the Zoom people actually said it's okay. Now, of course, they said it's okay now. I felt maybe you have to reload or maybe you have to join again. Bola Tops or something like that. Please, maybe you should refresh your page or something like that. So let's go back to the explanation. As I said, this is a practical thing. In fact, bring out your phone and let's try to relate with this thing. I know that some of you already understand what I'm saying, but still, let's carry everybody along. If you open your camera phone like this, me, I'm actually opening my phone. Now, mine is currently in 1. The ratio aspect or the ratio level is actually in 1, meaning that 1 zoom or 1.0 zoom, or I don't know how you call it. Now, you discover that just take note of the extent. Also, take note of the details that you're actually getting from when your phone is on. So like this, I bring out my phone and I'm actually pointing to a details. There is actually a banner in front of me like this. You get? Now, it's capturing those information. I can actually see those texts in that banner in one. And I can see the extent at which this particular one is actually captured. Now, let me take you to 2. I want to zoom down to ratio 2. I zoom it down. What do you discover? You discover that the extent compared to 1, what happened to it? It reduced. And what happened to the details? It becomes clearer. Does that make sense? Please, I need you to react to this, especially this particular phase that we are in currently. That immediately I zoom to 2 like this, I take it to zoom to 2. I increase the zoom level to 2. What happened is that the extent that one was covering before, that was not the extent it's covering again. It has shrink. It has reduced. But however, for the fact that it has reduced, there is a clarity. I'm seeing this thing clearly. The words that is on the banner that I'm actually talking about, it becomes more clear. I can read the word more clearer. If I take you to 3 again, what will happen again? The extent, the size, it becomes what? It becomes shorter. It becomes shorter. The extent, the coverage extent becomes shorter, and I can see more details. Now, mind you, I know that some of you might be saying that the more you are zooming, the more it's becoming blur. Which that is so, in fact, that is not even actually the case. The more you are zooming, the more you are supposed to be seeing the details. If what you are doing, if you are zooming in and it's becoming more blurry, then probably you are using ITEL. Sorry, no, not my word. Sorry about that. What I'm saying is that if you are zooming in and the details you are getting is becoming more blurred, just know that it is actually the quality of your camera. Because the ideology is that the more you are zooming in, the more you should be able to see those details, especially something that is actually written. So does that make sense? Sorry for ITEL users. Sorry, I don't mean to. I don't mean that. So that is exactly what spatial resolution is. So you have to now understand that each satellite has different spatial resolution. Meaning that, for instance, Landsat data has something we call 30-meter resolution. Meaning that in a single picture, now satellite does not zoom in or zoom out just like our phone. That was just a context. Satellite does not zoom in like the way I'm zooming in. Satellite sensors or cameras are what's called constant. Okay, you get. So it means that in a single, so I'm talking about what's it called now? I'm talking about what's it called now? I'm trying to explain spatial resolution. So I'm now using Landsat satellites for an instance. That how it works is that how the satellites works is that they capture image at an interval at a temporal resolution. We are still coming there. Meaning that you know that the Earth surface is big. Okay, don't let me even go to satellites. Drone, for an instance. If drone is operating, drone cannot capture, especially if your area is big, your coverage or where you're trying to capture is a big place. For him to be able to capture that big space, to capture it at once, what will happen? The drone has to go up. And in that case, the resolution of that particular drone is becoming more bigger. Please, you need to take note of this. And what I'm trying to explain again is that, let's assume maybe I need details of 2 centimeters. Now, in cases of drone, or even in satellites, there is an altitude that needs to be set for me to be able to get that resolution I'm looking for. So if I set my drone on my satellite that I need 5 meter or 5 centimeter or 5 meter resolution, there is an altitude set. So if my land area is big, maybe I'm trying to cover the whole of United States of America, for an instance. Now, the satellite most time cannot capture the whole of United States at once. So what it does is that it keeps taking picture. Now, I hope you know that. Satellite actually orbits around the Earth. Satellite are not stationary. Am I right? Yeah, satellites are not stationary. they move as the Earth is actually moving. Sorry, am I correct with that term that I just used now? Brentford, can you help me out with that statement I just said now? That satellites are not stationary. They move, they orbit around the Earth. Please, I need someone to confirm that statement. Okay, someone said yes. All right, thank you very much. Thank you very much. So it moves. So let's assume maybe that satellite or drone is passing through, what's it called? It's passing through the United States of America. It will not just cover the whole of United States of America at just one single shot. No, it goes bit by bit by bit, minute by minute, and keep capturing that picture. Keep taking that picture, keep taking that picture. So where spatial resolution now comes in is that at a single shot of Landsat data, the extent is 30 meter by 30 meter. So, for an instance, if you have a land area of 100 meter, now I'm just saying for an instance, a land area of 100 meter. So if you bring, or if you are making use of this satellite imagery or something, this is just an example. So it might not be able to capture the whole of 100 meters at once. So what it does is that because of its own mission or how it is being set, it can only give you 30 meter by 30 meter at once. Meaning that the extent of it will be like, okay, just look at this image on your screen. Just look at this image on your screen. This is the whole, what's it called? This is the whole place like this. This is the whole, let's assume this is the whole place. What spatial resolution is now saying that at this single shot, this square you are seeing like this at once that you are seeing like this, that is spatial resolution, meaning that is a defined shape, a defined extent. That is what spatial resolution is. So where the terminologies is now, or where the technical is now, is that just like I explained the phone aspect, the camera phone aspect, is that you have to know that the each satellites don't have the same resolution. Now, Landsat is different from Sentinel. Now, Sentinel Landsat can take up to 10 meter resolution. Now, from what I've explained so far, if a satellite has a resolution of 10 meter and a satellite has a resolution of 30 meter, what do you think the difference? What do you think the difference is? Like, what, in terms of their attributes, what do you think that the difference is in this data? Let me see if someone can actually get what I'm saying. Like, I just asked a question, I just want our response. A satellite has a spatial resolution of 10 meter. Why another one has a spatial resolution of 30 meter? If you get this data, you download this data, what do you think the difference in this data in terms of their attribute or their physical, the way they look? What do you think the result will be from what I've explained so far? Can I see your comment? Someone said 10 meter is better than 10 meter is a better imagery. Okay. Yeah, I agree with you to some extent. To some extent, but Mr. Mefford, to some extent, I agree with you. Yeah, 10 meter is actually okay. I really get what he's saying, but when we start moving to some deeper analysis, you will start having to understand that sometimes especially if you are working with drone, you start knowing that sometimes better resolution or good resolution or low resolution does not actually mean that your project will be successful. But I get totally what he's saying. 10 meter gives clear resolution of picture compared to 30 meter. Good, okay. The satellite of 10 meter will capture finer details. Thank you. God bless you, Miss Jennifer. The satellite of 10 meter will capture a finer details than 30 meter. God bless you so much. One will have a larger details than other. God bless you, Samson. 10 meter by 10 meter resolution will be clearer and more details. Thank you. But you are supposed to complete that statement that 10 meter by 10 meter resolution will be clearer, more details, but small size. Assuming you've added that, I could have given you 10 over 10. Yeah, it will be what? It will be clearer. It means that at 10 meter resolution, I can see details. I can see details. It can be more clearer. But however, the extent has what? It has shrink. I don't know how to put that right. The one with less number of the meter of meter, the 10 meter has higher resolution and it has more details. Thank you. But please complete it. Yeah, it has more details. But however, the extent is what? Small. Sure, you get the point like that. The extent is small, but it has a final resolution, good resolution, detailed resolution, but the extent is what? Small. So it means that if you are working, or if you need something, if you need an imagery that, you know, that has to do with a large extent of an area, like you need something big. Well, maybe when we start moving to some analysis, like maybe land to land cover, you start knowing that even though 10-meter resolution has its own implication, it has its own, because the lesser the finer the resolution, the more capacity you actually need, the more storage you actually need. But let's leave that for now. One result will be better, and one will be of good quality. Yeah, thank you very much. Now I think my explanation is actually it's okay. Now you get my explanation well. 10-meter is clearer image. Yeah, so basically that is what spatial resolution is. You guys already get my explanation. So let's go ahead to, so number 2, we have spectral resolution. For example, 1 meter resolution equals to each pixel represent 1 meter by 1 meter. Okay, you may see individual buildings. Yeah, thank you very much for this example. Now look at the example that Mr. Mefford is saying. He says 1 meter resolution, meaning that each pixel represents 1 meter by 1 meter on the ground surface. So it means that as at 1 meter resolution, it's possible for you to be seeing buildings. I mean, you should be seeing buildings. You will see every details you need to see. Meanwhile, in 30-meter resolution, each pixel represents 30 by 30 meter, meaning small buildings. In fact, at 30 by 30 meter, you might not even see any buildings. What you'll just be seeing is, don't worry, I'll show you soon. Yeah, thank you. I think I'm good to go. Now, spectral resolution. Oh, time is gone. Time. Wow, we've spent close to 2 hours already. Spectral resolution. I say spectral resolution refers to the sensor ability to distinguish between different wavelength intervals. It represents the bandwidth of each spectral band, the sensitivity of detector, the finer the spectral resolution, the narrower and the wavelength range for each band. So what am I saying exactly in this spectral resolution? I say, for example, multispectral sensor. Okay, I think I will explain that later on. So what I'm saying is that where spectral resolution comes into play is that the how will I put it like this? I'm looking for a better way to put it. Now you can have for an instance, I'm looking for a best way to actually explain this spectral resolution. Spectral resolution is just talking about the ability for you to be able to distinguish between the slightest change in an object. That when you have, for instance, if you have a data that it is of 12 band, compare it to when you have a data that it is of hundreds of band. That hundreds of band gives you the more ability to be able to distinguish between a feature. So you might have an image, you might have a data that it might be difficult for you to be able to pinpoint that, oh, this is it might be able to be difficult that is this water, is this building, but when you bring in the spectral concept, the spectral now help us to fine-tune all these details, to give us more details. So spectral resolution is majorly talking about in colors. It majorly talks about colors, the differences in colors. I don't know if that makes sense. Let me see if I can get something from here. The more wavelengths a sensor can separate, the better it can tell different things apart. Like water, thank you. The more the wavelength inside that sensor, the more you can be able to differentiate between objects. Spectral resolution equals to how many different colors or energy sensor can tell apart. Thank you very much. That's just a simple way to put it. So spectral resolution tells you, it is the one that actually tells you in terms of color, the energy, that, oh, this one is building. No, this one is vegetation. No, this one is forest. No, this one is so and thing. That is what spectral resolution is. So I don't really want to go into details. Now, the third one is radiometric resolution. Radiometric resolution refers to the sensor ability to detect small differences in energy intensity. It describes how finely a sensor can measure the brightness level e.g., 8-bit equals to 256 brightness level, 11-bit equals to, or 12-bit image equals to thousands of brightness level. Higher radiometric resolution allows better detection of suitable differences in reflectance, such as slight vegetation stress, minor moisture variation, small temperature differences. So maybe you can say radiometric is something similar to what's it called, to radiometric. Radiometric is similar to spectra, but they are actually different. So in radiometric, he actually tells us or allows us to detect some slight, what's the best way to differentiate this from spectral signature? I'm looking for a way to differentiate this from spectral signature. So can I use the concept of 8 bits of bits? I believe that we are familiar with our system. Sometimes you see that your system you'll be seeing that your system is 64 bits, your system is something bits. Okay, hold on. Oh, sorry. Okay. Let me see if I can get something for you from here. The more wavelength a sensor. Okay, no, that's not what I'm looking for. Okay, yeah, I think I'm just looking for a better way to make them differentiate between spectra and radiometry. So he said that radiometric tells how many the brightness level. Yeah. I think that's right. The brightness level of an object, while spectra tells the kind of light it is. I really I really want you to get the difference between these two, even though they sounds familiar. I mean, radiometric and spectra, they sound familiar, but it's different. Radiometric test, it talks about the brightness level, the sensitivity to brightness, to what's it called, to light. Is that the correct word now? While spectra actually talks about just like what was it called, what Mr. Medford said, the kind of light that it is. So don't get it confused, even though, as I said, they are actually bit related, that they are bit related. So lastly, we have the temporal resolution. The temporal resolution refers to how often a sensor revisits or captures imagery of the same area. Now, here is what temporal resolution is actually talking about. Also, know that each satellite, all the satellites I'm mentioning, the Landsat, the Sentinel, which are majorly the common ones, as I said, they are configured separately. Their configuration or their making is totally, they are different. But one of the things again that you should know is the fact that, I was trying to explain that the satellite actually moves around the Earth's surface. So what temporal resolution is now talking about is that the ability for a sensor, or for a satellite to go back to where it starts. So for instance, if this is where the mission begins, or let's assume maybe this is a particular place that it started from, this is a particular location, and remember that it moves round, right? It goes round. So temporal resolution is not telling us that is defined as a revisit time, meaning that the ability for this satellite to be able to move around the Earth and go back to that same particular location it started from. I don't know if maybe you get that. For it to move around, so it started in point A. The satellite started from point A. So temporal resolution is not talking about the ability for it to go round B, C, D, F, G, down again to return back to A again. So one of the things that you have to notice is that this temporal resolution varies across different satellites. You have to take note of that. And now, you see, there's a reason why I'm taking my time to explain this 4 type of resolution. Because what I just said now, in the future, if care is not taken, this will affect some of your projects. For some of you went ahead to pick a project topic. Oh, let me work on this, and you are not considering, especially this kind of temporal resolution. This temporal resolution, when you start seeing the effect, is if you are working on something that has to do with what's the name of this analysis? Spatiotemporal analysis. We call it spatiotemporal analysis. I'm looking for a plain English. Why am I forgetting things? There's a simple word we call this spatiotemporal analysis. Time series. Yeah, thank you. Time series analysis. Meaning that you want to, what's it called? Time series analysis. You are trying to revisit past data. Maybe you are working on, for instance, you are working on an analysis that has to do with you actually going back in dates. Like you are trying to go back in, maybe you are trying to know what happened in January, what happened in February, what happened in March, what happened in April, May, June, July, and so on and so forth. That is what we call time series analysis. So if you don't know the temporal resolution of the satellite imagery you are looking for, you might have issue. So for an instance, Landsat satellite, Landsat data had a revisit time or temporal resolution of 16 days. Am I right? I think I am right. 16 days. So meaning that what that 16 days is telling you is that it takes 16 days. It takes 16 days for that satellite to go from point A back to point A. So meaning that if you want a data of point A, if you want the data of point A, maybe across time, it means that you always have to wait for 16 days. 16 days before you can get that data. Because that is what Landsat will take for you to be able to orbit around the Earth to go back to where it starts. Sentinel has a temporal resolution of, please, is this 3 days? No. Sorry. Sentinel has a temporal resolution of what? Is it 3 days? Mr. Mefford, please, if you have that information, let me paste it. Yeah, 2 to 3 days. Okay, yeah. Actually, I think it should be around 3 days. Is it that fast? I didn't even know that Sentinel actually has that much temporal resolution. So Sentinel has 3 days resolution, meaning that it will take 3 days for Sentinel in satellite to go from point A back to point A, 3 days. I think there are actually even some data that takes 1 day. Yeah, I think there are satellite that takes 1 day, that has one day temporal resolution. MODIS, for an instance, I think MODIS is also 1 to 2 days as well, if I'm not mistaken, as well. You guys can just drop in the comment section, just put in the comment section, both YouTube and LinkedIn, the type of satellite we have and their temporal resolution, for learning sake. Back 2021, I do IT with a company that uses remote sensing to capture imagery of the farmland in Pakistan. But the imagery spectrum comes every 7 days. Yeah, that is what we call, that captures the remote sensing to capture, that comes out every 7 days. That is what we call temporal resolution. That is temporal resolution. That is the revisit time of that particular platform you guys are actually using. So all these satellites, they are structured or they are designed differently. There is even a one that uses 30 days. That is only 30 days, meaning that before you can get another data again, it's the next month again of that same particular resolution. And one of the things again that you have to know is that is not even only the inch about this thing. Well, when we get to the analysis, I think I will explain that. Okay, GOES 19. It's a geostationary weather satellites operate by now, that can observe target area and the frequency of about 30 seconds. Yeah. Look at what Mr. Mefford is telling us here, that there's a satellite called GOES, GOES 19. That is a weather satellite data. So that kind of data, you cannot use that kind of data. It needs to give us reports, timely reports. So it does not make sense if the temporal resolution of that kind of satellite is now 13 days, 16 days, or 3 days. So there has to be a timely, a hourly or minute or seconds temporal resolution. And Mr. Mefford is telling us that it has a 30 seconds temporal resolution, meaning that it gives us information of that particular area every 30 seconds. And these are kind of satellites that is actually used to predict, used to know the weather condition, used to predict, used to forecast, and so on and so forth like that. So is that clear? So those are the major 4 types. So let me read what Mr. Mefford actually typed here, said here, easy memory. He said, anytime you hear the word special resolution, just know that he's talking about how detailed is my data. If we are talking about spectra, he's saying that how many kinds of light. When we are talking about radiometric, he's saying how many bright how many brightness level, and we are talking about temporal. How often do I get my data, or how often is the data being available? Does that make sense at all? Yeah, spatial, the size of the object that can be detected, spectral ability to distinguish wavelength band, radiometric sensitivity to brightness differences, temporal frequency of image acquisition. So, does that make sense? Can I move on? Okay, I think I can move on now. So there are two type of sensor or two type of imagery, anyone you want to call it, but most time we often call it maybe two type of sensor. Now you need to know, meaning that all the sensor that is mounted upon the satellite to capture the information that we need, they are in two forms. We have the multispectral and we have the hyperspectral imagery. Okay, there's actually a need. So number one, the multispectral imagery is a remote sensing data collected in several wavelength band of electromagnetic spectrum, such as blue, green, red, near red. Each band captures specific information, which I've actually explained that earlier. Typically contain 3 to 10 spectral band. Or I think that information is not totally correct because Landsat 9 actually has about 11 bands or more than that. Used for application like land cover mapping, vegetation, water body detection, and urban analysis. Provide good general classification, but with limited spectral details. In simple terms, multispectral gives multiple view of the Earth. Multispectral gives visible multiple of the Earth using a few distinct spectral range. While in hyperspectral imagery captures data in hundreds of very narrow continuous spectral band, which allows very detailed identification of coming back. Sorry, hold on. Okay. So, which allows very detailed identification of material based on their unique spectral signature, contain hundreds plus of narrowband, enable precise material, commonly used in advanced agricultural mineral exploration, and so on and so forth. Basically, what I'm saying between multispectral and hyperspectral is there are differences in band. One has a narrow band, one has a continuous band. So just look at this image you are seeing here. So this is more like how a bispectral band looks like. I can see that it is continuous. While in multispectral, I can see that it is divine. It's specific. I mean, is that the right word to be specific? It's always not like between the range of 3 to what's it called to maybe 11 or 12 or something like that. But when it comes to hyperspectra, you can have hundreds of it, and the application actually differs. So in multispectra, if you are doing something like just a normal crop, vegetation monitoring, water body analysis, or band analysis, your multispectra is actually good to go. But when you start entering into some advanced analysis, like you're trying to do something like mineral exploration, advanced environmental monitoring, that time you might now want to start considering using hyperspectral sensors, and which is not actually cheap and is not really sometimes available. Yeah, it is finite. Yeah, thank you very much. Is there any question or anything I need to answer? All right. Okay, so data acquisition. Now, this is where we move to the practical. Let me see if I can finish this class in the next 30 minutes. So, data acquisition and availability. Now, I said something strongly. Now, we are entering into more like the practical section. You might want to get your laptop ready and, especially for those of you who have not watched the class. I said every project usually begins with a clear title. Please take note of this. I choose my word carefully, and anytime you see me place emphasis on this, because I know that as time goes on, especially those of you that are kind of dedicated, that will be dedicated, all this information are very essential for you to know. I said that every project usually begins with clear title, number one, aim, objective. In GIS, however, the success of your project often depends on the availability and the quality of your data. That might sound funny, but that is very true. You can have your objective, you can have your aim, just like our final year projects where we write our objective, our aim, I want to do this, our research question. But in GIS case, truth of the matter, I don't know if maybe you agree or you do not agree with me, that for you to be able to achieve your objective, it is dependent on, number one, if the data is available, and not only that, the quality of data you downloaded, you have to get. Now, what I mean by quality of the data, automatically you should be able to refer back to the four type of resolution that we have. So that's what I mean by quality of the data. And don't worry, I will show you more about that. So in GIS, that's actually sometimes the cases. I mean, there are some projects that you might just abandon because why? There's no data. There might be data, but that data is not useful to use. Sometimes what you plan to achieve must be adjusted. I don't know, this sounds very funny. That sometimes what you plan to achieve must be adjusted based on the type of data you can access, where you obtain it, and how reliable it is. It's fact. Sounds funny, but it's fact. Very fact. Fact that there are times that you just have to adjust with what you have, especially in GIS. Data acquisition refers to the process of collecting data and so on and so forth. So, a recap from our course 2, which we did last week again. We have three types of data: the vector data, the raster data, and the attribute data. I'm not going back to that again. You might go back to course 2 if you didn't join the class. You might go back again and watch the video again. So I said there are two sources of data. We have the primary data and secondary data, which I believe that everybody should know. The primary data, what is it talking about? These are the data that you collect directly from the source. These are the data you yourself you collected. Direct data from source to hand. That is what we call the primary data. While secondary data, it is you trying to leverage on the platform that has gotten that data so that you can have access to it. Is that clear? Primary data, I'm the one that gets the data first hand through maybe you going to the field, through interview, it is you conducting the interview, so you are having the information first hand. That is what primary data is talking about. While secondary data is you going to a site, a platform to fetch those data. Those are secondary data. So, I mean, limitations can be expensive, time consuming, and all, and so on and so forth. Okay, okay, all right, no problem, Mr. Mefford. So, okay. So let's now talk about vector data. So the question now is that what we want to look into is that how can we now start downloading this data? I need to round up this class anytime soon. So that how can we download this data? So let's start with vector data. Now, know that there are various places, various sites, various platforms that I myself did not even know they exist that you can actually get your data from. But I'm just going to show you few of where you can actually get this data from. Few platforms that I'm aware of, I know, and it's trusted that we can actually get this data from. So I believe that in as much as you are enrolled in this course, you should have access to this slide. So all these link or all this platform is actually embedded inside this text. So once you click on this, it will take you directly to the site. Once you click on this, it will take directly to the site. So let's look at one. Number one is called OpenStreetMap. So one of the places you get your attribute data is OpenStreetMap. So let's look at how OpenStreetMap actually looks like. I want to open this in another window. Please, we are downloading data. I mean, I might not download data here. But go back and watch that video, the costly video, which is on the LMS or the link that has been shared on the group, and go and watch how to download data, because the data that you download is the data we'll be using starting from next week. Please take note of that. So this is OpenStreetMap. OpenStreetMap is a open source, what's it called? Open source data bank where you get your vector data. And please take note of take note that what are the three types of vector data that we have? Polygon, line, and what? And point. So it means that anything that has to do with polygon, for instance, our administrative boundary, our river data, road data, and so on and so forth that has to do with vector, we can able to download it from here. Can be able to download it from here. So how do I download data from here, from OpenStreetMap? Actually, I prefer downloading this. If I want to get the data from OpenStreetMap, I prefer using QGIS. So actually get from QGIS, I prefer using QGIS to actually download my data than me actually coming down here to download the data. But however, let me just show you how to download your data. So let's assume that now we are already inside a practical aspect. So please, if you have your system with you, you might want to practicalize along. So let's assume I want the road network, the building network, everything that has to do with any vector information that has to do with this particular area. So I'm making use of this particular location. For instance, this is inside Oyo State, Nigeria. So I want to download both the road data, the building, or any other features that is there. All I need to do is come to here, export. You see up here, export, click on export. And you can decide to, if you know the extent or the area of interest or where you are working on, you can, if you know the coordinates, you can just impute the 4 coordinates and impute it. But if you don't know the 4 coordinates or the coordinates, you can just click on manually select a different area. So once you click on that manually select a different area, you automatically see that there is a box, more like a box that is actually on your screen, that actually appears on your screen. So you can now decide to adjust, depending on the area you're actually working. So let's assume maybe, okay, let me just zoom down to this school. I'm seeing a school here, Ajayi Crowther University. So let's assume I need the data for this school. All I need to do is, I can move it around, know the extent I want. If I want it smaller, anything. So just look around it, just make sure that it captures the whole area of your interest. So I think I'm okay with this, since this is just a practice. So yours, you can extend yours. Then after that, all you just need to do is to click on export, and automatically your data should start downloading. As you can see, my own there is telling me that did I want to download it. I'm not actually downloading it, but once you just click save, you get your data, which you can now use in your GIS environment, for instance, your QGIS environment, and you can start doing your analysis. So that is one. That is how OSM works. Maybe I'll still show you how you can able to do the same thing from QGIS. So that is how, so you can see how very simple and seamless it is to be able to get data. So where is my slide? Wow, where is my slide? Oh, I don't find my slide again. Okay, well, let me just go ahead. So other site I think I included there is called Diva. Is it Diva or Diva? I don't know what you call it. So just put that. No, I think I need that slide. I need that slide. So that I've made it easier for you guys. Just click on the icon. It should give you your what's it called? Okay, I've seen what I'm looking for. So this is the second one again. So just click on it, and it will take you directly to the site. So for an instance, here you can select the country you want. So for instance, let me go down to Nigeria. I will be downloading Nigeria. Please, for those of you practicing, for those of you who are actually following along, please, you can, I think if you've watched the video before, one of the things that I kept emphasizing on is the fact that you can download your own, and you don't have to download what I'm downloading. It's the same process. If you are currently in Zambia or Uganda or Kenya or Ghana, you can download from your own country. It's not necessary to download the one I'm actually downloading. But let me download Nigeria. So I will trace Nigeria. This is Nigeria here. So it's asking me that what did I want to download? Subject. So you see, we have the road data, we have the elevation data, we have the land cover data, we have the population data, any data you want to download. But I want to download, let me just say I want to download administrative boundary, administrative area, meaning that the boundary of Nigeria. That's what I'm willing to download. So as you can see, he told me to download. So in this kind of case, now this is more like the metadata of the data. So you can actually check the details here, this is what it contains and so on and so forth. And here you can just click on download, and automatically your download should begin. So depending on the data you are downloading, that will determine the size of the file that you are downloading. So I've downloaded that one. So as you can see, there's a lot you can download. If you are trying to do something that has to do with railroad, you are trying to do something that has to do with water, you are trying to do something that has to do with elevation, land cover, these are your guys here. You can just come down and download. So another one I have again here is Grid 3. Yeah, I so much love this site. Grid 3. So just click on the link. So I so much love this site as well. Is a vault of data. I mean, it's a bank of data, a lot of data that you can actually download. You can see boundaries, infrastructures, population, sentiment extent, settlement point. You see the data they have here. You can see risk analysis, social distancing data, boundaries, population, and so on, and so on, and so on. So I can decide I want to download the population data. So just click on population. Oh, no. Oh, no, that's not what. Just come here, population, click access. Is this the same thing? Yeah, good. Once you just click on that access, you can see they even categorize their own data, special integrate displacement data, gridded population estimate, population 3.0, 3.1. So in this kind of case that you have various kind of data. Now, this is where your metadata now comes in. Remember, the information of the data, this is what will back you to know the right data to download. So for instance, this population version 2.0 is telling us what it contains. This data feature gridded population. So as you can see, is a gridded data. A gridded data is a grid data. You know that, for instance, population data can be in terms of Excel formats, just country, male, female, and so on. So there is also a format that is also in form of grid. Here you get. So just make sure that you read through what's it called? You read through the metadata, the information of the data, before you go ahead and download the data you're actually looking for. So once you are certified, just click on it and download the data. The downloading is also easy. I clicked on version 1. Let me see what version 1 is saying. So as you can see, in fact, one of the reasons why I love this Grid 3 is that it's going to show you how the data you're trying to download, how it actually looks like. Oh, come. Okay. Okay. Yeah, as you can see, so you have to read all this, they also put summary here. You have to, read everything one by one to know if you are downloading the right data. Then after you are certified, you can now go ahead and download. Where's my download button now? Yeah, download the format, any format you want. Can click here and download. Then your download should begin that way. Your download will automatically begin that way. As you can see, my it has begun. Then I can use my data. So that is that about that. Which other one again? Google Earth Pro. I believe that some of us should be familiar with Google Earth Pro. Google Earth Pro sometimes is used for visualization or to pull out data sometimes. Please, are you guys still following? I'm not seeing any comment again. Are you guys still following? Nope, I've not lost you guys. Okay, thank you very much. You guys are still following. Thank you very much. So this is how Google Earth Pro looks like. This is how Google. I had a problem with my laptop. I've not been able to follow. Kindly share with me lesson 3 and please. Kindly check your email. The link to the LSM is actually in your what's it called? In your email. So kindly check your email again. You will see the access to the LSM. So as I said, one of the thing of this Google Earth Pro is for visualization. So you can just decide to go anywhere, to visualize. Also, you can even pull up your data from here. You can pull up data coming. So you can just go anywhere and what's it called? Go anywhere, visualize what is going on. Let me try to zoom in and see what is going on here. As you can see, and one of the reasons why I love this 3 is the future of the 3D. I mean, you can be able to visualize all this in 3D. So for instance, if I using this tool called Street View, I can just bring it here and input on the street, then I can be able to see the 3D of how this particular location actually looks like. Can you see? Now, this is what we call remote sensing. This is what we call remote sensing. You see, I can see all this place and I'm not physically there. So I can actually tell you what is going on here. That's what we call remote sensing. I mean, I can keep roaming around the streets without being there. That's the beauty of it. I can keep roaming the streets. I mean, I can keep going. You can try it at your hand as well. You can try it at your hand as well. I mean, I can see what is happening. I can see what is going on. I can see the kind of building that is here and so on and so forth. So I said, you can, let me go back again. You can use it to pull up data. So let's assume maybe I zoom to this area and I type filling station here. Let me see if it's going to fill up filling stations. If I click filling stations, it's just like Google Map. So automatically it will tell me all the filling stations I have in this area, as you can see. As you can see them, as you can see, all the filling stations, all those red things you see are filling stations. And I think I should be, I've not actually tried to download, but I know that I can be able to pull up a data. All these filling stations I see can be able to pull them up from there. Yeah. So that is Google Earth Pro. I mean, there's a lot you can do. There's a lot you can do. And we'll be making use of it when we start doing land use land cover analysis for verification purposes. I mean, this is what's it called? This is a airport. Am I right? Yeah, this is a airport. As you can see, it's very detailed. This is a plane. I mean, as you can see, so it's also a place to pull up your data and so on and so forth. So let me move on. So we also have and so on. Yeah, so there's a lot of places you can download. So what I want you to do is please go and download the data. Download the data. Did I include that in your assignments? I don't think I include that. So explore all these particular sites and try to download one data or the other. If you're having issue or you don't understand, kindly share your screenshot on the group, and I believe that people will help you out. So now let's move to raster data, and I think that this is where things actually gets complicated and we can actually call it a day. So there are also a lot of various sites, but because of time, I will only be showing you 2. So as you can see, we have from NASA Earth data. Please go and watch the video. The LSM video. Please go back and watch it because I'm trying to round up now. My time is gone. I've spent quite numbers of time here, so I need to go. So go back to that video and I showed this for instance, this NASA Earth data. I demonstrated that you can download your data. This one, I also show how you can get your data and so on and so forth like that. So I'm only interested in these 2, USGS and Copernicus. I'm only interested, and we will be downloading data, and this data, mind you, will be using this data that we are downloading here, we'll be using it in course 5. So you might want to pay attention on how to download this particular data, how to go about it. So clicking on the number 1, which is what we call the USG Earth Explorer. So click on it. Once you click on it, it will take you directly to the page. I've actually saved you the stress on you trying to navigate your way to the site. So once you click on it, you'll be able to get there. So now this platform called USGS is actually the bank of Landsat data. This Landsat data that I've been saying since morning, that I've been shouting this since morning, Landsat data. This is one of the sites, one of the place or the major place you get that Landsat data. I don't want to, okay, maybe once you start the analysis, I might start having to explain to you that we have various kinds of Landsat data. We have Landsat 1, Landsat data. I mean, all these Landsat, they have an expiring date. Yeah, let me just put it that way. They have an expiring date. I just don't want to bore us with talk. I could have actually started explaining the rudiments behind the how this satellite are being configured and all. But one of the things is that most of the satellite has expiring dates, meaning that if a satellite is launched now, there is actually a period of time the satellite can use to operate. So that is why if you search online like this and you search type of Landsat data, you'll be seeing things like Landsat 4, Landsat 5, Landsat 4, 5, 6. At the moment like this, we have Landsat 9 is currently in operation. Landsat 9 is currently in operation at the moment. So Landsat, basically what I'm saying is that, for instance, Landsat 7 was able to capture data, was able to get data from the period of 1990 something to, I don't really know the year, to so period. So when you get to that particular state, the satellite was discontinued. Is that the right word to use? It stopped receiving data. So they launched Landsat 5. So Landsat 5 also collect data from one period to another. Then it goes to a point to stop. So they launch another satellite and so on and so forth. So the one that is currently running and is still collecting data at the moment is Landsat 9. And so now this information I just said now, it influence one decision in whatsoever analysis you are trying to do. This should automatically tell you that, okay, if I want to work on a project that has to do with maybe year 2010, that automatically gives you the idea that, I might not be able to use Landsat 9. Why can't I use Landsat 9? Because Landsat 9 started its operation in year 2017 or 2018 or thereabouts. So it means that there is no Landsat 9 data that is available for year 2010. So it means that I have to go back to maybe Landsat 8 or Landsat 7 to be able to get the data of year 2020 of year 2010. Does that make sense to you? Now, let's go to how can we now download our Landsat data from this site. So if this is your first time of using this particular site, Earth Explorer, USGS, the first thing you might want to do before you can be able to download data is to register. You have to register, you have to sign up. And the sign up is, even though if it is long, but it's still straightforward. So you said you can see what is going on there without being there. Are you implying seeing what is going there in real time or according to stored data? Now, what I just showed you now is according to stored data, but also have the understanding that it is possible that you also see what is happening in real time. But here is the catch. Nobody has access to that kind of satellite or that kind of data. The only people who have access to a real-time data is the government and the military personnel. Just know that. That is my own knowledge for a while now, that there is a real-time satellite that collects a real-time data, but we don't have access to that kind of data. Only the government officials or the military people have access to that kind of data. But this data, for instance, I showed you, they are stored data, as you said, they are stored data. So I can be able to know what happened maybe 1 month ago. I can be able to know what happened 2 months ago. I can be able to know what happened 5 years ago. I can be able to know what happened 10 years ago, and so on and so forth. Does that clears your answer up, Mr. Chiji? Okay. I don't know if that clears your answer up. So the first thing you want to do, as I said, if this is your first time, please, I might just rush through some things here. So if truly you want to, if truly you want to download data, you want to get something done, please go back to that video. That's where I think I took my time to explain in details how to go about it. So if this is your first time, just create a new account. So I already have an account, but let me just show you how the account. So you'll be asked various questions. This is not the only, but just keep following. The what's it called? The process is, the setting up is easier, is easy. Just keep following the instruction. Any question they're asking you, just keep answering it. The questions does not affect maybe your registration will be approved or not. Just keep answering it, and at the end of the day, you will get your username or your your username and your password and all like that. Then you can now be able to log in. But as I said, I already have a login details. As you can see here, this is my username and this is my password. I cannot even remember because I already saved it. So I will click sign in. So once you create an account and you successfully create an account, you can now log in. So once you log in, and this is what you will also be seeing once you log in. So let me log in from here. As you can see, I'm logged in already. Ajayi Firm, I'm logged in already. And this is how the portal looks like. I'm not able to download course 4.2. The PDF returned and it is in the author's bin and therefore not downloadable. The video is extremely 19 gig. Please help sort out. Mr. Nicholas, number 1, this is course 3. We are not dealing with course 4 now. So let's deal with course 3 now. And I don't know why you should be able to access course 4 from the LSM. Please use the LSM. If you cannot get it from the, what's it called, from the link. I will check again, Shabo. I think people are already watching course 4 already, so I don't know why yours is. Well, let me leave that. Don't let me get distracted. As I said, this is actually course 3. I didn't do course 3 now, not course 4. So how do you now download your Landsat data? So please, this is practical section. So I really wish you guys follow so that, this data we're about to download like this is what we are going to use for our next class. Please take note of that. So the first way, as you can see from this left hand of mine, you can see we have something like select geocode method. Once you click, we have future DNS, we have address, we have pattern row, we have the future name, we have the state, we have the future type, and you can see a lot of them. So for you to be able to download your data, there are 4 steps that you need to go through. Number 1 is selecting your area of interest. Your area of interest. The portal wants you to want to know which area are you trying to download, which area do you want to download, which area are you working on. So there are various methods to actually do that, to actually geocode your area of interest. But one of the features out of these 3 options, one of the options I will advise is to use address and place. Can you see address and place? Though if you know the pattern row, there's something we call the pattern row. I don't want to go into that. If you know the pattern row of your area of interest you are trying to use, you can also use your pattern row. All you just need to do is just to impute your pattern row. Maybe your pattern row is 118271. You impute it here, then it will take you automatically to the place. If you know your future, your DNS, you can also impute your DNS and so on and so forth. But the most one that is mostly easier to use is address. So for instance, after clicking on that address, I want to download data of, let's say, Lagos. So all I just need to do is to type Lagos, that particular place. Then to bring out the option for me, as you can see, it's telling me Lagos, Nigeria. So I will just click Lagos, Nigeria, because that's where I want to download. Then I will click show. Once you click show, it will automatically give you something like this. You can see it will show you address and place, the latitude and longitude, and all you have to do is just to click on that particular thing. As you can see from my keyboard here, from my mouse here, just click on it, and once you click on it, automatically you discover that in your Canva here, it automatically create a drop bot sign, a location sign, meaning that it's telling you that this is the location that you are trying to download. You can see, so this is Lagos. For instance, this is the entire of Lagos. This is Lagos. As you can see, this is the boundary of Lagos. So it's telling me that this is the Lagos. Then after that, remember I said that there are 4 processes. Are there 4 processes? Yeah, I think there are 4 processes. So after that, the second process is now to now tell the portal wants to know that, okay, this data you are trying to download is for which period? Which period are you trying to download this data? So let's assume we want to download for January 20. We need the data that is in between January 2026. So we come down here to date range. Then we click on this calendar icon, and to bring out the calendar. So 2026 January, anything from January 1 to January 31st. So what I'm technically saying is that I want any data within the month of January. So if peradventure you are working with if peradventure maybe your analysis actually has to do with you downloading a specific date. So all you just need to do is to specify that specific date. But mind you, you might not get the specific date. So, but what the prompting I did here, what I'm trying to tell the portal is that I need any data within January 1st to January 31st, meaning that any data that I share in January in my area of study, which is Lagos, give it to me. Then after you set it, you will see something like set date. Then click on set date. Oh, okay, before you go there, now the next step after the first step is what? You're coding your address, your area of interest, where you want to download data, the area you want to download data. The second one is to set your date range. Which date are you looking for? The next one is to choose a cloud cover. Now, I was saying something earlier about quality data, and now I think if you are someone who has been following and actually understand what remote sensing is so far from my explanation, you're able to know that one of the limitations of space-borne platform or space-borne remote sensing or satellite imagery is that for the fact that they are launched thousands of kilometers away, there will always be some hindrances or some obstacles like cloud cover, meaning that there might be some period whereby there will be a cloud in that particular area of interest that are trying to download. There will be a cloud cover that is actually covering that particular area of interest, and satellites do not really have the ability to penetrate, especially passive remote sensing. They don't have the ability to penetrate through cloud, unlike active remote sensing like LiDAR that have the ability to penetrate through cloud. But in satellite imagery like this, they don't penetrate cloud, meaning that it will capture both the cloud and your area of interest together. So, as I want to download this Lagos State, for instance, if this particular dates that I've actually selected, if there is a cloud in that particular period of time, I will not be able to see the future. So I will only be seeing the cloud. I will not be able to see the future that I need under, like the real future. Maybe I'm trying to, see the buildings, see the river or something, or any future. See, the presence of cloud cover will not allow me to access those information. And in that kind of case, that data might be rendered useless. In fact, it will be rendered useless. I think I gave a clear example in the video I did. Please go back and go and watch that video. In the third video, the raster downloading video, I showed you a clear example of how a data can be useless, how you can download, how cloud cover can, how cloud cover can make your data, render your data useless. So in this kind of case, I want to make sure that all the data I want, it should just be within 0 to 0.5. I can decide to set it as to 1. I can decide to set it as 0. But note that what you set will determine the result you get. So if I leave my cover range, a cloud cover range to 100%, I will get a lot of data. But not all those data will be eventually useful. So what I'm doing is I'm trying to streamline my results. So it means that I don't want any data that is from 0. Maybe let me just leave it to 0.10. I don't want any data that is from 10% down to 100%. I just want a data that is between 0 to 10, that has a cloud cover of 0 to 10%. That is the data that it is useful, that I can use. So let me just set it that way. Let's try to see one and maybe you understand better. Then after that, then the fourth step. Remember the first step, code your address. Number 2 is that your date range. Number 3, your cloud cover, which is very extensive. And lastly, select the data you want to download. So as you can see from here, the data is in various types. I mean, the classified data, digital elevation. I mean, you have the various data, but the one we are interested in to download at the moment is called Landsat. As you can see that I say something that Landsat has a lot of data. I mean, it has a lot of configuration, different kind of data. Please, sir, at what point does radiometric correct cloud maxing technology etc. comes in? At what point does radiometric correction, atmospheric correction? Yeah, I think I will. Let's see. Let's just go ahead. Maybe I will try to explain that as time goes on. Now you see, I don't. This. Let me just go ahead first. I really don't want to divert because what you just asked like this now, you are moving more like the question you just asked, Mrs. Jennifer, if I'm correct. We are moving now into the technicality analysis part. I mean, when you get your data and you start having to perform some corrections on it. But I don't let me divert at this moment. Let's see if I will still be able to answer your question as we move. So the one we are interested in, as I said earlier, that there are various kind of Landsat data. So one was actually launched called level 1. That level 1, something happened to it. I think they say the sensor was not okay or something like that. So they launched level 2, and I think the difference between level 1 and level 2 was that there was an upgrade in the sensor, or there was a correction. Was it radiometric correction? They did something with it. Yeah. So mind you, if you are trying to download your data, it is advisable to go for your level 2, Landsat collection level 2 data. So as you can see in level 2, we have Landsat 4 to Landsat 5, meaning that if you are trying to get the data from how do I put it now? Remember I was explaining to you that all these satellites, Landsat 4, Landsat 5, they all operate within a duration. So Landsat 4 and Landsat 5, I don't know, as far back as 1990 something, 2001, and so like this. So if you are working on a data in 2000, year 2000, just know that you don't have business coming to Landsat 9. You need data that has to do with Landsat 4, Landsat 5, because you are working far back data as 2001, 1990 something, and so on and so forth. So you can just make your research that, year 2005, my analysis has to do with year 2005. What Landsat actually covers this year 2005, just search and you can be able to get your answer. So let's just go ahead and download Landsat 8 or Landsat 9. So I will select Landsat 8 and Landsat 9. I will tick it. This is what I need. Then after that, all I just need to do is just to click results. So automatically the algorithm will look for a data for me. It will look for a data that what is called, to look for a data that fit into what I've actually selected. You understand? Now, if you look at the result it brings out here like this, you understand? You discover that it only brings out one result for me. And the reason why it brings out just one result for me is because of the parameters I set earlier. So I said that I want a data from within the period of January alone, and the class cover has to be 0 to 10. Now, see what happened if I change that settings. I'm coming. See what happened if I change that settings. If I go back and I increase my cloud cover to, let's say, 58%. I increase it to 58%. I click results. You see something now. You see how many data it actually brings out for me. No, if I increase it the more, it will still bring out more data. If I set my date range, the whole of year 2025, anywhere in year 2025, I will see hundreds of data. So here is now the implication of what I was talking about now. Remember that I set my class cover at what? At 0.5. I set my class cover at 0. From 0 to, I think, maybe 80. Now, look at this result. Let's view one result. Let's view one result. So once I click on this icon here, I'll be able to see. So here in this particular each option that is bring out, you will see something like footprint. This footprint is to, once you click on that footprint, is to tell you the extent at which your data covers. So let's assume maybe you are working with the whole of Lagos. For an instance, if you are working with the whole of Lagos like this, now the boundary of Lagos, I'm coming. Now, this is the boundary of Lagos. See here. So that is why I didn't show you, maybe later on, I didn't show you that you can also use your shapefile, your boundary to actually download data. So let's assume I want to work with the whole of Lagos, for instance. Let's assume I want to work with the whole of Lagos, for instance, and this is the boundary. I know Lagos very well. This is the boundary of Lagos. So now you discover that once I click on that footprint, you discover that it's not covering some aspects. It's not covering some aspects in Lagos. So this one is only telling me that this is the area. So I now have to look for another data again that actually now covers for this particular area, then merge it together. But that is an advanced something. I don't really want to go into that. But let's just stick with what we have due to the practical sake that we're actually having at the moment. So the footprint shows me the extent. If I click on this next one, so what does this next one show me? It shows me how the data looks like. Now, this is what we call cloud cover. Now, can you see all this white thing you are seeing? It is cloud. Now, can you see what I'm saying now? Cloud. Can you see? So automatically, this data is useless. You cannot use this data to do anything. So, Mrs. Jennifer or Miss Jennifer, you are asking about atmospheric correction or something like that. No matter the kind of correction you want to apply to this data, it doesn't make sense to apply any kind of correction to this data. I mean, there are specific analysis you can do to correct atmosphere or cloud corrections or something like that, and something. That varies. I mean, there are other variables and other factors to that. But I'm saying that there are kind of data that no matter how error the data is, no matter the correction you are trying to apply, is useless. This data automatically is useless because if you check the metadata of this data, okay, let me just go ahead. Oh, comment. Does this show? Now, this one, what does this next one show? Compare browser, no. This next one, yeah, if you move here, you see something like show metadata. Remember that I tried to explain metadata. What is metadata again? The metadata is what? The data of the data. Information about the data. So if you look into, and if you are downloading data, it is very essential to always check the metadata because it's the metadata that will inform you about the kind of data that I'm actually downloading. So this kind of data like this is telling me that the name of this data is called Landsat 8. This is Landsat 8 now. How do I know if this is Landsat 8 or Landsat 9? Oh, my time is gone and there's actually a lot to this thing. Please, you guys have to, I think I will be stopping here very soon. So you guys have to go back to the LSM and go and actually watch the complete video. So you see this particular name, this is the name of this particular Landsat. And you see all these numbers you are seeing, they actually have that definition, they have that meaning. LCO8, meaning Landsat 8. This is Landsat 8. If it is Landsat 9, you will get it will be LCO9. If it is Landsat 7, it will be LCO7. That's how we know the kind of Landsat we are downloading. Followed by the level. Automatically, this is talking about level 2. If it's level 1, it will be L1. Followed by the pattern row. This thing you are seeing here, this 919055 is the pattern row. The 119 is the part, while the 005 is the row. Now, this is not the date. The date of this data that this data was captured or this satellite captured this data is year 2026. 01 is talking about the month, which is January, and 04 is actually the what's it called? It's actually the day. So meaning that this data was captured year 2026, January 1st, 4th of January 2026, and so on and so forth like that. Data acquired, as you can see for here, is even here. Data acquired 260104, category T1, collection 2, collection number 2, pattern row. You see, this is the pattern row. You know, all these things are, if you are into remote sensing, I believe that you can even actually, like, all these have they actually have their own meaning. Now, you can see start time. This is when they started collecting data in that area, and this is when they stopped collecting data to move to the next place, as you can see. So, anytime you come to this metadata, one of the things you want to check is something I call cloud cover coverage, and this is it here. As you can see, he's saying cloud cover. He's saying that this data that I'm about to download has 54.68% cloud cover, meaning that data is useless. you should not get any data between anything that is between 0 to 0.5, at most 0 to 0.10. In fact, there are some data that are 0 and that are 10% that are even useless. I don't know, maybe you get what I'm saying. As you can see, 54%. So it is actually useless. So without wasting much of our time, I just needed to show you that. So let me just go to, so this, look at this first data like this first one. Let's look into this first data. Let's see what this first data is. Let me cancel this. So this first data, I think this was the first one actually brings to us. This was the first one it showed us earlier. This was the first one that it actually showed us earlier. So let's look at how it actually looks like. So if you click on the footprint, you will see that this is the footprint. This is showing us the footprints. So let's look at how the data actually looks like. So as you can see that this one actually even has a little bit of class cover. You can see that there's even a little bit of class cover here. But then you can check the metadata. Now you can see the data here. So if you zoom here, you could see some little white cloud cover, meaning that this area, if you are doing something related to this area, that data is not really useful. But if you look at this upper part, all these other upper parts, you see that it's free from cloud cover. It means that if your area of interest is around this particular area of interest, it means that this data is good for you to download. Now, there's also some technicality to this thing. There's some technicality to this thing. And one of the technicalities is that you might be asking, how can I download the data that is actually free from cloud cover? Now, one of the understanding that you have to know is that you have to know that seasons, it is actually what brings about this cloud cover. Meaning that in Nigeria, for instance, I'm staying in Nigeria for instance, there's something we call the harmattan season. Is there another word for harmattan season? Please, if there's another word for harmattan season, let me know. In Nigeria, I'm not talking about harmattan season. And that harmattan season, there is always a lot of fog, a lot of cloud cover in that particular, and it always happens between January, December, January, February. So it means that any data you are downloading in those particular periods, there is high chance that cloud cover might be included in those data, especially in rainy season. No, sorry. I think I confused it. It is actually in rainy season that you get more of cloud cover. It is actually in rainy season. I think cloud cover only happens in harmattan season earlier in the morning, like that. But once it is now maybe 10 o'clock, 11 o'clock, everywhere is always clear. So, and that satellite it might be maybe that period that I might start capturing that data. So you are good to go. So what I'm basically saying, and I hope that you don't miss my point, is that how you know that, though sometimes you even have, you are not even at liberty to actually even choose sometimes, depending on what you are working on. But I'm just giving context about what actually brings about this cloud cover. So if you need a data in the course of the, rainy period in Nigeria, our rainy season is always September, August. I mean, that is when rain is always more heavy. So you have a high tendency or high chance that your data, that there will be a lot of cloud cover in your data, compared to when you are downloading maybe from March, April. Now, because of sake of time, I don't want to go back. If I search a data from March, for instance, March, April, you will see that most of the data I will get will be clean. I mean, you can try it at the end of at your hand. You can try it at your hand. You see that most of the data you get, just set 0 to 0.5. You see a lot of data that will bring out for you that is clean. So I'm trying to say that sometimes seasons are what sometimes brings about this issue of cloud cover. And I said, once your data is full of cloud cover, it is useless. So because of sake of time, because I should have actually rounded up since we can go ahead. So once you click on the metadata and you see that that you are good to go, that you love this data is okay to what you want to do, all you just need to do is just to come to this icon here, download option, and it's going to bring out your download option for you. Click on this product icon, then you can see you download all your full data here. if maybe what you need is band by band, which I'll be explaining that later on, maybe when we start our analysis. So if what you just need is just one single band out of the whole everything, you can decide to look for the band and download. But it's always advisable to download all your whole data together. And as you can see, for this particular one, is coming with 884.23 MB. So if I click download, it's going to actually download. But I have the data already. I'm not going to download it. So at your own end, please go ahead and download because you will need the data. So go ahead and download. You can decide to choose any of your area of interest. So have I communicated something that actually makes sense this morning? Have you learned something? Please let me know. I'm trying to round up now. I struggle to download land cover data from Copernicus. The download icon is not showing, or maybe you didn't get to find your way around it. Please, sir, at what point? Okay, I've answered that question. I asked because some regions such as Niger Delta usually have like, yeah. Do you know I was actually even about to mention that? I was actually about to mention that. That is because, you know, water, there is more of water activities, more of kin activities in Niger Delta. That is why you always see data with high cloud cover. So it's an issue. That is an issue with optical data, especially when you have to depend on satellite data. I mean, currently, there's one analysis that I'm currently on like this, and what has made me pause on that analysis because I need satellite imagery. So actually, I need satellite imagery, and I could not get one useful information, one useful data to use in that particular in Niger Delta you just mentioned now. So there is no any useful data that I've been able to get so far. So far, so good. But however, now one thing you should know is that I'm not sure I didn't mention of it is that the Landsat data and Copernicus as free. As you can see, you are not paying any money. Just go there and download. But there are some satellite imagery that are free of cloud cover, but most of them are not free. Take note of that. Most of them are not free. They are not free. I think I encountered one of recently. I think that should be on LinkedIn, ComSat or something like that. I mean, a fine resolution, but it's not free. All those kind of data cannot be free, of course. They cannot be free. So that's one of the challenges you have. That's one of the challenges you have. So it's usually very rare to get an image with less than, yeah. How do you navigate that challenge? Won't atmospheric correction and cloud cover technology surface? As I said, yeah, they can surface. But if you get my explanation, as I said earlier, that there's still limits. You see what you mentioned there, they are more like an advanced topic in remote sensing. That's why I'm trying to avoid not to actually go there, because I mean we call it, I'm trying to look for the name we call it. Remote, maybe if I remember, Sha, that is an entire course on its own. That is when you start having to talk about filtering, you have to talk about slicing, a lot of techniques in actually correcting all these things. And one of the disadvantages about all these particular things you are doing is that in the course of you trying to do all these things, information might be lost in your data. Something will be altered in your data, and so on and so forth like that. So I'm not saying that it's not possible they can surface, but I'm not still telling you that there is even a limit to how all these things can work. You can't tell me that all your land use, all your data you download is about 50% cloud cover, and you are trying to use atmospheric correction to correct something. It's not possible. You will lose data, and I mean, assuming I want to get the location of some communities in the local government world, how can I get that using OpenStreetMap? Download the whole. Now, I showed you earlier when I was trying to download the administrative boundary. So download the administrative boundary of, even though there are some sites that you can even download that local government you are looking for, that word you are looking for, it gives you the privilege to be able to download that particular word or local government that you're actually looking for. But however, in case you're unable to get that, you can download the administrative boundary of that country that you are working on. So the administrative boundary, anytime you download the complete administrative boundary, it needs, as I'm supposed to show you, but time cannot permit me again to show you. Maybe when we start the analysis next week, then I can show you. So in the administrative boundary, it contains the shapefile of the whole country, it contains the state level, it contains the local government level, and it contains the world level. So from that administrative boundary, can I extract that particular word or that particular local government you are trying to work on? That is how it works. Could you please show us how to select only one area to download in Copernicus? It shows only global. I don't have that time again. Is there other website to download variable land cover data? Of course, Earth data, just search online. There are a lot. Just type it online, and I also impute some in the slide. There are a lot of them. Let me check it. Anson, can I get someone for peer-to-peer learning? Code season. Okay, I think there's not any question on the YouTube. So that is how to go about your data. That's how about. So see, Landsat data can be very challenging, especially if you are, I mean, it can be very challenging. I won't lie to you. I mean, and that is why the invention of what is it called the invention of Kenya actually comes to play. Of drone technology has to come to play. I mean, drone technology, cloud cover cannot affect drone technology. Well, to some extent, it cannot affect. So I mean, if your project is very concise, I mean, just get this UAV, fly around the area, and you can be able to get that particular data that you're actually looking for. I mean, it's because of time I was supposed to do comparison between UAV and satellite imagery. So UAV is just more like a mini satellite. So it gives you, I mean, control over your resolution, over your other parameters. So in fact, instead of you having 30-meter resolution, 10-meter resolution with drone, you can have as low as 5-meter, 0.2 centimeters resolution, and so on and so forth. So that is all about that. So guys, go ahead and download the data and let me know the challenges you are passing through. So I think I really need to round up. I've spent over 3 hours. No, this is a lot. Let me see if I can open Copernicus and. So please, if you have any question, please drop it as I'm rounding up. Also, please kindly do well to follow us on LinkedIn. I mean, I say LinkedIn. Yeah, do also follow us on our social media page, LinkedIn, IG, YouTube. Kindly subscribe, please. All these things, I always say, all these things does not take much from you. Just few seconds and few clicks. Please, I think that's one of the best things you guys can actually do for us. Kindly follow and. Please, are we going to get the class link? Of course. Please, where can we get the administrative boundary you are referring to? I demonstrated it now. I practicalized it now. When you know it in class, I practicalize it. Go to the slide or go and rewatch the video again from the LSM, or go get the slide and you will see I input all the links for you to be able to get them. What else again? Try SG2000 land cover data. Yeah, there's that. Is there other website to download variable? Please, could you show us how to select one area? Okay, is there? Please, if you have any other question, please just drop it now and so that we can call it a day. As I said, please do well to follow us on our social media page. Those of you on the YouTube link, please. I mean, there are a lot of people of you currently watching on the YouTube. I mean, all of you and most of you have not even subscribed, you've not followed. Please kindly do that. God bless you as you do that. This present live link, is there going to be, of course, it will be sent to the group. So this is Copernicus. Let me see if I can just do something within 5 minutes. So of course, you need to also register for Copernicus before you can able to download your data. So all you just need to do is log in and have account. So if you don't have account, you just have to sign in. You can see here, register, follow the procedure and register. Once you are registered, then you can log in. So this is mine already. I have an account. So this is how Copernicus. So remember, Landsat in USGS, the Earth Explorer, the one we just finished now, you only have access to your Landsat data. While in Copernicus, you have access to your Sentinel data. I think I explained the difference between these two data before. They are both satellite imagery. They are both imagery. They are both raster data. The only difference is their resolution. Their major difference is their resolution. Landsat data is 30-meter resolution. Why Copernicus data, which is the Sentinel data, it gives you the access to 10-meter resolution, 20-meter resolution, 30-meter resolution. So depending on what you are working on, for instance, if you are working on something that has to do with vegetation indices, vegetation analysis, you need a better resolution, like 10-meter resolution, and so on and so forth. So please make sure you download Landsat data because you'll be needing it, and also make sure you also download this particular one. So they recently changed the Copernicus browser. It was not like this before, so I understand that it might be really bit technical to actually go about and be able to know how to download. in fact, go back to the video. I took my time to also explain how to get your data from this. So let me see if I can demonstrate something. So also, firstly, you need to set your, what's it called, your study area here as well by creating an area of interest, or you can actually download. I mean, bring in your shapefile, but you see, once you click on this edge, so you can draw a polygon, you can draw a rectangle, or you can upload your area of interest, meaning your shapefile. But let me just draw a rectangle. Let me just draw a rectangle. Let's say yeah. Okay, let's say yeah. As you can see, so here is my study area. So the next thing I want to do again is to set my date range. Let me set my date range. I'm just picking any location. Jesus, look at class cover. But this is just the picture. That's not. So let me set my date range. My date range, January, 1st of January to, I'm coming, better still, I'm coming. Yeah, just click on this. I want to select a range. That's why. So I want it from January, just like what I did in the other, let's say January 1, then on to that same January, or I can even decide to increase it to maybe February 31st or anyone or any number. So after selecting my date range, the next thing I want to do is to look for my product. I mean, what am I trying to download? So all I need to do is, you see, I don't have time to start explaining this. One of the beauty or one of the advantage of this Copernicus is that you can download your NDVI, some of your, normal, what we do is all this data we're downloading, we take it to GIS environment, we download it, take it to GIS environment and start analyzing our softbox. This Copernicus site has given us the ability to download some indices like NDWI, NDSI, and so on and so forth, instead of we trying to do the analysis. But that is not my focus. That's not what I'm trying to download. So as you can see, this is Sentinel-2A. So let me just increase this. So we have Sentinel-2, we have Sentinel-1, and so on and so forth. I told you that Sentinel-1 is your SAR image, your SAR, while Sentinel-2 is actually the optical image. Then after that, I go to coming. Coming. Okay, I click on search. So after you select your date, okay, let me even go back. I think I forgot to show you something. Yeah, this class cover, I can see this class cover is in 30%, but let me try to reduce it to maybe 10%. So you see also the same procedure like the USGS. You have what? You start with your area of interest, your date range, your class cover. You just select your Sentinel-2, or you can just come to search here. You see, we have Sentinel-1, Sentinel-2, Sentinel-3, Sentinel-4, Sentinel-6, and so on. Please note that all these sentinels are all different. This Sentinel-1 is the SAR. Sentinel-2 is the optical. Sentinel-3, I don't even know what that is. Sentinel-5 is actually a data for atmospheric, is it atmosphere? What's the right word to use like this? What's the right word to use? If you are trying to know like the earth hazard, the atmosphere hazard, something like this is your guy here, Sentinel-5P. I mean, all those Sentinel actually has their function. Thank you, sir. 3 hours of talking. God enlarge you. Thank you very much. God bless you, Miss Janet or Mrs. Janet. God bless you. Thank you for the prayer. Please, how can you use remote sensing to draw a map? How can you use remote sensing data to draw a map on your study area? I don't know what you are saying, but when we get to the analysis aspect next week, maybe we can understand. No, from my end is okay. No, I can see your screen. You two people, what are you saying? No, sir, we are not in the WhatsApp. I'm not sure if people say are actually working with me at the back end. So actually, don't worry, it will be sent to your mail. in as much as you are registered and you register, we have your mail, and I think I'll personally forward and those are like the WhatsApp link that I'll be forwarding are only for those who are not in any of the group. So if you're in any of the group and you see the WhatsApp link, please kindly ignore and please don't join for the sake of those who are not yet on the group. So we are not on the what is the difference between EVI and NDVI? What is the difference between EVI and NDVI? Please wait for course 5. I will explain that in course 5. That is when we start doing vegetation indices. Then I'll be explaining those type of indices for you. So, okay, let me just rush through this. So what we want to download is our Sentinel-2, MSI, cloud cover. Please reset your cloud cover back to like 9% or 10%. What we are interested in is our 2LA. I don't have time to start explaining that again. 2LA. Just click on this L2A. This is what I set. Sorry. January 1st, 2026 to March 25 or so. Then click on search. I hope you guys are flowing now. I'm downloading it. Please, as I said, though I will still the data we are going to be using for the analysis, I will still include it in the what's it called course lecture. But please, there will be a point that you have to use your own data that you download. So it's searching. So as you can see like this, look at the various options that this thing actually brings out for me. So one of the things I love this one is that you see this grid that actually comes here. All this grid is trying to show you all the data that is available. So this first one here, as you can see, look at this first one here. This first one here. So I can check the details of this first one here. Or you can just click on one. If you click on just one icon, remember that this is my study area that I selected. So it's bringing all the data that is available inside my study area. So if I click on this, when you zoom in very well, take note, you have to be very, very careful. This is my study area here, 1, 2, 3, 4. But it's telling me that these are all the data, meaning that there is not one single data that actually covers my whole area of interest. Do you get that? There's not one single data. So it means that for me to be able to get all the whole data that covers my whole single of data, I have to download everything, then I'll go and merge it together in a GIS environment. Does that make sense? Thank you very much. I believe that makes sense. But let's assume I want to download this. Let's download my area of interest because of sake of time. So once I click on it, you see, it's bringing out various options for me. And look at the first one. If I click on the details of the first one, it shows me the metadata, just like the other Landsat. And from this metadata, I can be able to check my cloud cover as well. So let me go and check my cloud cover from here. My cloud cover. Where's my cloud cover? You see, look at this one. Our cloud cover here is saying 0.0. So it means that we have 0, like we have more like nothing cloud cover, which means that this kind of data is what? Is good to fly, it's good to go. So once you are certified with it, all we do is what? We click download and our data begins to download. So I think I've answered the question. The person that said that is having issue downloading data from Copernicus. I think if you watch this, I think it's very straightforward. All you need to do is just once you log in, you sign up, come to search, define your area of interest, define your dates, click on your area of interest. I mean, very straightforward. You might want to actually rewatch the video again, but I need to go now. So, guys, what else again can I go? I think I've tried. Yeah. If you guys say that I have not tried, I've had you, but I know I've tried. 3 hours class. I mean. So, guys, is there any other thing again? Can I go now? Please, your thumbs up, your comments. Thank you so much to Miss Rejoice. God bless you as well, too. God bless you. Thank you, sir. Monday. Mr. Monday, thank you. Well done, sir. We appreciate your effort. I also appreciate you for staying till this time. Mr. Banmitele Bolodu, if I'm right about that. So thank you for the lecture. Mr. Kenneth, thank you also. God bless you. God bless you all. See you in the next class. So please submit your assignments. I've said this. Stop being worried about either your assignment is being approved or not. Stop being worried. In as much as it's showing pending, it shows that you've submitted. I mean, it's not easy to start approving. Do you know how many of you? So it's not really that easy to start approving assignments one by one. So don't worry about the pending. I mean, someone was even dropping it on the group that is discouraging that they've not approved his assignment. I mean, well, let me reserve my comment. So please, the assignment is not stopping you to proceed to the next stage. So I believe that by tomorrow, all the assignments should have been submitted. Everybody should have concluded course 3. Course 4 is already open. Go back to the LSM and start course 4. Now, course 4 is pure practical. Course 4 and course 5 is pure practical. So you will need your QGIS, you will need your data, you will need, hand-on experience, because what you'll be submitting in course 4, I really want to see that you guys are really doing what the practical aspect. I won't say much, but know that starting from course 4, I will start rejecting assignments. If I look very well into what you do and I see what you do is not okay, I will reject the assignment. You have to redo it again. So please take your time, watch this video. This is when things will start getting more serious, because it's, as I said, it's pure analysis. I mean, this week like this course 4 like this, you're having 2 project analysis to work on. So please take your time. Same thing as course 5. So our next live class will be on Friday. Friday again, 5 to 7. Then possible Saturday morning, 9. I can't even recall the time again, but the time will be communicated on the group. So please take care, guys. God bless you all. Thank you very much. God bless you all. Have a very wonderful night rest. For those of you who are actually at night, I know that some of you are actually in the morning. So, all right, take care, guys. Bye.
And this is 10 o'clock on my end. Thank you so much, Dr. Ajayi. We are grateful.
Thank you very much. God bless you, sir. Have a wonderful night rest, sir.